Good morning. We are starting session 5 now that is titled Mission and Campaign Designs. And we are starting with the first talk by Philip Lubin titled Directed Energy for Planetary Defense. So, welcome.
Yep, okay. I spent part of yesterday at the University of Tokyo and went out afterwards with my host, and we drank a fair amount of sake. And apparently I messed up. So there's some things here which are not quite right. I left off one of my students' posters, plus I misspelled somebody, so I had an excellent night. Okay, if you're interested in the details of this, go to our website. You'll find over 20 technical papers over the last few years. So I'm not going to spend too much, oops, let's see, that doesn't work either. Let's see, just hit space bar. No.
Is this a PowerPoint?
No, it's a PDF.
PDF? Let me see here.
Yeah, there it goes. And out it goes. Okay. All right, great. Okay, so photonics is a little bit different than impactors or other methods, and I want to talk about this just a little bit. First of all, photonics is an exponentially growing technology, unlike other propulsion methods or the other things being discussed here. So it's very, very different. It's more like electronics in that sense. It has a doubling time of about 20 months, very much like the so-called Moore's paradigm in electronics. Okay, in this system we use directed energy to create effectively a plume, a rocket engine on the target, either a comet or an asteroid, and that provides the fuel, so we don't take fuel with us. But the problem is that you have to consider this as a long-term program. There are two types of ways in which the system plays out. One's a stand-on system, which you actually travel to the target, which is the same as all the other programs being discussed here except for this one. The second, however, is a complete standoff system. So you leave your system at home, which really is part of a longer-term development program, which is being sponsored by NASA as part of our relativistic propulsion program. But the point at which you enter this exponential growth curve for photonics is critical in terms of the economics of this large-scale standoff system. This system, unlike the others, I don't mean this in a demeaning way, but it's a multi-purpose system. One of the systems happens to be planetary defense, but others are space debris mitigation, beam power, active illumination of the solar system, composition analysis, which we just got a NASA phase 2 on, asteroid mining, rapid interplanetary travel, et cetera. It's the same system. You only build one. So that's nice because you can amortize it, not just having a system waiting for the next thing to threaten the Earth. Also, you can do high-fidelity lab tests, which, as was mentioned a few minutes ago, are a little more difficult than some of the methods. And you can amortize the system over the entire mission space, which is not just planetary defense. It also enables comet defense. Okay, and so I think one thing to think about is this is a long-term program, and one should think about it. The threats are not just tomorrow. Okay, let's see if we can do this. That doesn't work. Okay, so really it's momentum transfer after, not energy. So you can't really compare these things together. Momentum and energy are really quite different here. So if you calculate the force per unit power, in the relativistic case, it's gamma over gamma minus 1 v over c squared. On the non-relativistic case, it's basically just 2 over v. So this lower the velocity, the more efficient the force per unit or momentum transfer per unit energy. And the worst possible is to do photons, unless you do something with the photons, which is what you do with nuclear weapons and with laser ablation. So for a given energy, the highest momentum transfer is at the lowest speed. and you just want to exceed the escape velocity from the target you're at. So the conversion of energy to momentum depends on the interaction physics. So there's two types here: direct momentum transfer, like impactors, gravity tractors, IBD. Second is laser nuclear, where you convert the energy to ablation. Okay, so just for example, an impactor, which might be a modest one, 10 tons at 10 kilometers per second, is of order 100 meganewton seconds, and an energy of about 500 gigajoules. A laser, for example, has a coupling coefficient of about a tenth of a millinewton per watt, or 100 newtons per megawatt, which we've measured in the laboratory. And to get 10 to the 8th newton seconds, like the impactor, would require about a megawatt for about 12 days. However, this system can run continuously, so if you left it on for 3 years, you'd actually have something equivalent with which is roughly 100 impactors divided by the beta factor. Okay? And over the same 3 years, you get about 25 kilotons delivered to the target. Okay, so there's two ways forward here. One is a short-term, we'd call DE Starlight, which is something of 10 to 1,000 kilowatt system. 10 is actually relatively small compared to a tactical system. And the other is a long-term, full-blown standoff system, which is what we're trying to develop as part of this relativistic propulsion system that we're funded by NASA in a phase 2 through the Breakthrough Foundation and through some private entities. You may have seen some more stuff in the media. It makes nice science fiction looking things. But okay, so directed energy comes in, and then it goes into different channels, some which is conduction into the body, some is radiation going back out, and some of it is mass ejection. It's the mass ejection which you're interested in. When you make a plot of vapor pressure versus flux in watts per square meter for various materials that might be relevant to asteroids, you find that they enter a linear regime at about 10 megawatts per square meter. So if you want to take away a number, you want the illumination to be greater than 10 megawatts per square meter. This is two different cases. This is for asteroids versus comets. The relevant line is the black one here. This is in thrust in per watt. And what you see is you have photon pressure here rising to ablation pressure, which goes up here. And typically it's about 10 to the minus 4, 10 to the minus 3 newtons per watt. When you go to water, this is high temperature material like SiO2. When you go to water, you see the same kind of curve in black, but notice the flux is very different. Instead of being 10 megawatts per square meter, it's now a few hundred watts to a kilowatt per square meter. So you can hit a comet at vastly greater ranges, which you really can't deal with other types of mitigation strategies. So this is a kind of an ARIS conception, if you will. It looks a lot like ARM because it looks a lot like ARM. Except on the front end, you have a phased array laser system. And here's your target. Okay? So you use the asteroid as fuel. You don't need to take much fuel with you. All right, we've went through a bunch of different configurations. I'll just show you some of the designs going into up to about half a megawatt in an SLS Block 1 deployment. These are the ATK Megaflex options, which they feel quite comfortable going up to 30 meters. These are various launch vehicles that we've looked at. And this is the power class, again, up to about half a megawatt, although there's no reason they have to stop there. ATK happens to be about a mile from UCSB, our campus. So this is a 10-meter solar panel. Okay, this is what it looks like inside of a fairing. It fits. You can go easily up to a megawatt or even 10 megawatts if you want. I think what's interesting is to look at something like Apophis. So this is the laser time on versus mist distance in Earth radii. This is a 3 delta V. This is 1 delta V. This is a simulation of the orbit. And what you see is, in order to get to a 2 Earth radii, you need about, say, 16 years with a very small system. This is a 30 kilowatt system, which is not very large. Okay, you can deflect targets. This is up to 500 meters with various classes of laser. This is electrical power, actually. And this is the deflection time in years. So, for example, a 200-meter asteroid would be deflected in about a year using a half megawatt class system. Okay. Here's launch off the launch pad versus electrical power that you can put on board. So here's a megawatt, and you need to take off about roughly 20 metric tons off the launch pad. Okay, so an SLS Block 1 gives you 70 metric tons, which is about up to 3 megawatts, or roughly 1.5 megawatts of laser power. SLS Block 2 would give you 5 megawatts. Here's an impactor comparison. So just bottom line is, this is a 100-ton, which is a huge impactor, compared to the same launch in directed energy. It would take less than a year with directed energy. Here it would take about 10 years with an impactor. So directed energy actually is a very, very powerful way of mitigating various types of things. Here's Apophis again with a very small mission. This is a 100 to 200 kilowatt class system, and it takes of order 6 years of exposure to get a 2 Earth radii deflection. Okay, SLS Block 2 of this would take less than a year. Okay, we went through various cases. This is a short time response, 40-meter diameter, where you had 17 days to respond. Okay, so here you need a full standoff system. You don't actually go to the target ever. This is about a 15 megaton air blast equivalent. Same thing, here's a 40-meter diameter case, 4-month response. And again, you'd either need a megawatt class system to go to the target or a full standoff system. This is a very tiny system, a 20 kilowatt, operating on Apophis. It's about a 15-year standoff. Okay, what about comets? There's a nice poster if you're interested, Zhang et al. And take a look at that. The bottom line is you can actually deflect large comets. Here's a 3-kilometer diameter comet, and you can see if you had of order 10 to 20 minutes per day of exposure of the system we're talking about for large-scale directed energy systems for relativistic propulsion, you could actually deflect it. Here's a 60-kilometer Hale-Bopp-like comet, and you need of order an hour or two per day to deflect it. You can start deflection at 10 AU because you don't need much flux. We do lots of laboratory testing. We also have a phase 2 for composition analysis. We looked at rotating asteroids, and one interesting thing here is you can use the same system to de-spin an asteroid, which would be very useful if you want to land on it. It's just the amount of time it takes. And there's a whole set of papers on this if you're interested. Okay, conclusions. This allows a possibility for planetary defense. It's a very different type of technology. There's lots of low-hanging fruit, space debris, close approach targets. The technology is exponentially increasing, so it'll catch up fairly quickly. If you're interested, you can check out our website where we've got about 20 papers on planetary defense and about 50 papers on other topics. So I'll stop there.
Thank you. Time for a question with a quick answer, please. Microphone.
Please tell me a little bit more about the lasers that you're assuming here and their technology readiness.
Sure. Okay. So the question was, what about the lasers and the TRL level? So the lasers actually are not very large, because what you do is you do much like you do in a supercomputer. It's a parallel processing system. So this is a phased array. Each sub-element is roughly 100 watts to a kilowatt. Currently, a kilowatt will fit in your hand, and the current state-of-the-art is 5 kilograms per kilowatt, which will shortly be 1 kilogram per kilowatt. As you might imagine, these come out of non-civilian applications. But the technology does work. The current efficiency is around 42%. This is a ytterbium line. That'll probably rise to about 60% in the next decade or so, would be my guess. They've never been flown in space in this kind of application, so this is not for an immediate use, but I think it's something that you should be aware of as a community that over the next decade certainly could be developed. These are being used in tactical systems. That's becoming quite mature. For the large-scale case, for the NASA program, that's a very, very different kind of system. It's sort of a kilometer-class array and requires probably a 30 to 50-year build-out time. Uses the same technology, same small lasers. They're not big lasers. We're not developing megawatt-class lasers at all. They're actually very small. You put them in your hand. Now, they're laser amplifiers. Okay, they're fiber laser amplifiers, the baseline, which is ytterbium dope fiber, but we're looking at a number of applications. Yes. So currently we're at 1064 nanometers, but that's purely it's kind of the sweet spot in the efficiency today. We're looking at gallium nitride and other applications that would push the wavelength shorter than 1064. But something to be aware of, because planetary defense is not a one-year program. This is a long-term issue for the Earth. So you shouldn't just think of what you have today, but what you might have in the future.
Thank you.
Yep.
Thank you. We need to move to the next speaker, which is Yuichi Tsuda. Thank you. Okay. The talk is going to be about Hayabusa 2, sample return and kinetic impact mission to near-Earth asteroid Ryugu. Okay, thank you.
Okay, good morning. I'm Yuichi Tsuda, and my background is, sorry. Is that okay? Okay, so I'm now taking a role of project manager for this mission, but my original background is astrodynamics. And my talk is about the Hayabusa 2 mission, especially focusing on the kinetic impact mission, I think this is the biggest contribution to the field of planetary defense in this mission. And yesterday, already Dr. Yoshikawa presented about some part of Hayabusa 2, especially focusing on the scientific aspects. So I'm gonna focusing on the engineering aspects of this mission. So here's the highlights of the mission. So we launched the Hayabusa 2 in 2014, and it's now heading to the asteroid Ryugu, which is a C-type asteroid. And the spacecraft condition is very healthy at this moment. And it is a round-trip mission realized by high-specific impulse ion engine. And we will stay at the Ryugu for 1.5 years and doing in-situ science with 4 landers and 4 remote science instruments. And the biggest highlights for this mission is, of course, touching down. And we are planning to do 3 touchdowns, and 2 are what we call nominal touchdown, a normal touchdown, which is almost the same as what we did for Hayabusa 1 mission. And the third one is pinpoint touchdown to an artificial crater. So this artificial crater is to be generated by the Kinetic-Impactor device, which we developed newly for this, especially for this mission. And we expect to form a 2-meter class crater on the surface of the Ryugu. And with that, we expect to investigate not only surface of the asteroid, but also the subsurface information can be acquired. So this is a whole mission scenario of Hayabusa 2. We already launched successfully in December 3rd, 2014. And 1 year later, we performed the Earth swing-by, which was very successful and accurate. And now we are about here. So 1 year later, in summer 2018, we will reach Ryugu. And there we will stay for 1.5 years doing that touching down and the crater generation. And also we deploy 4 rovers on the surface of the asteroids. And then we will leave the asteroid in the end of 2019, and 1 year later we will return to the Earth in 2020. So this is a spacecraft overview. It's a very small spacecraft with only 600 kilograms. The main propulsion system is ion engine, capable of accelerating up to 3 kilometers per second. So that's the mission enabler for our round-trip mission. And in addition to that, we have a chemical RCS, which is a biprop system, which is for altitude control and also for the translational motion in the asteroid proximity phase. And here's a list of the scientific payloads. We have 4 in-situ remote science instruments like a multiband imager, near-infrared spectrometer, and thermal infrared imager, and also laser altimeter. And for surface access, we have a sampler and small carry-on impactor, which is to make a crater on the surface. and separation camera that is to observe the impacting process. And also we have 4 rovers. 3 are from Japanese University Consortium, a small rover with only about over 1 kilogram. But the other one is from our international partner, DLR Class, which is called Mascot, a 10 kilogram, very sophisticated lander. And what's the special feature of this this spacecraft is that as many as 12 deployable, let me say, robots are aboard the spacecraft. So to realize the surface access and roving and impacting and sampling, and also to complete the sample return by reentry capsule. So the target asteroid is Ryugu, which is a C-type asteroid, and with the size of believed to be a little bit less than 1 kilometer. And based on the light curve, we have this kind of a shape model, but we cannot fully believe this one at this moment. But if it's spherical, then it's very good for our mission. It's easier to touch down, but that's just a cross finger. And the present status, as of today, the spacecraft already traveled 22 billion kilometers. And the spacecraft is now almost at the L5 point of the Sun-Earth system. And the one small fun for us is that we tried to take a picture of L5 space from the spacecraft, so that just in case if we can find unknown L5 Trojan asteroids of the Sun-Earth system. So we already sent the commands to spacecraft, and the spacecraft already took a picture, but we are now waiting for the data to downlink. It's very faint probability, but why not doing this kind of attempt? So after 1 year later, we will arrive at Ryugu, and there we will stay for 1.5 years. That's very short for us. And one of the big challenge of this mission is that the asteroid environment cannot be acquired before arrival. So everything have to be started after arrival. So the quick scheduling right after the arrival is very crucial. So to prepare for that, we are now doing two kind of the preparation practices. One is the LSSP, or a landing site selection process that is participated by all engineering and science members of this mission. And the another one is what we call RIO, or real-time integrated operations simulation, which is basically real-time operation practice to do some critical operations like touchdown or crater forming using the spacecraft simulator, ground simulator. And here I will show you two highlights of the proximity phase. The first one is the touchdown operation, and maybe I will just show you the movie, because that's easier to understand. So after the arrival, we will try to touch down. So at the final procedure, we will deploy the target marker first, which is a visual marker, so that the spacecraft can autonomously track that visual marker. And spacecraft follows that marker and then touching down. Then at the touchdown, the projectile is ejected inside this sample horn, and the reflected soil will be collected and transported to the reentry capsule. And the second highlight is a crater forming operation. So we are using the EFP technology, explosively formed projectile technology. It's a pyro technique, but we don't want to use the pyro on the surface. So there is a standoff distance of about 500 meters, and then the liner, the pure copper liner, will accelerate to 2 kilometers per second at very short time, like 1 millisecond, and then hit the surface. And we are expecting to have a 2 to 10 meter class crater, depending on the surface condition. And before detonation, the spacecraft have to escape because to avoid the dangers. So to avoid the ejector or debris. So this is the movie for that. So this is the small carrion impactor. This will explode soon. And before that, spacecraft escape to the backside of the asteroid. And then explode and impact to the surface. And we made many experiments in the development phase, and I will show you just the biggest one, the full-scale model flight test in the abandoned mine in Japan. So here I set up the SCI, and this is the target. And so like that, it's a horizontal, flying horizontally, and then this is a high-speed camera image of the bullet, and then this is the final moment. And I think this is the most exciting one. Okay. Okay, so that's all I have. And the biggest contribution for the planetary defense is that we are pushing forward the boundaries of small body surface access, roving, sampling, impacting. So this is not a planetary defense mission, but for future planetary defense mission. Thank you very much.
Thank you. Again, we have time for one question and a quick answer. Anyone? Okay, thank you very much. And Cheryl. All right, Cheryl, it's all yours.
All right, thank you. Why don't we just leave it on? Is it working? All right, good morning. Going to give you a high-level overview of the AIDA DART mission. DART is the U.S. Component. You've heard a lot of talks already from many folks in our investigation team, and there's more to come. I'm teeing off a series of about 3 talks to come in this session. I want to introduce our team on the U.S. side. We have a Class A team from all over the country, both NASA centers and universities. And I would also mention fondly that it was back in Romania at the PDC that we first began our discussions about AIDA and creating such a mission, and here we are today. All right, you've seen this chart before, just to quickly show that when we conceived this experiment, we wanted to make sure it was as realistic as it could be with respect to the PHA. And so in terms of a kinetic impactor, you can see where DART lies, fits quite well statistically within the PHAs that we know about. This is one of our favorite charts. This shows the wonderful target system that Mother Nature has given us to set up this experiment. This experiment is a technology demonstration in many regards, not only to actually do the first kinetic impactor, but also with many of the technologies that we have on board of our spacecraft. So we have our Didymos system, twins. Our target is the smaller satellite, which is on order of about 160 meters. The primary is about 800. There's about 1 kilometer between the two. And the orbital period of Didymoon is about 12 hours. Now, when we hit Didymoon, we believe that we'll be able to affect the orbital period by about 7 minutes, and you're going to hear more about that from Andy Cheng when he follows me. I also want to say that we have several parallel programs going on, in particular our ground-based observation program that not only is occurring now during the development period to get as much observation time as we can on the Didymos system, but we were conceived such that in the event that our international partners were not there, which we very much hope that they will be, and will be much more of a rich experiment, should they be so, that we had to independently be able to make our measurement from the ground. And we have this opportunity of impact in the 2022 timeframe, for which we have both radar available and telescopes globally, down to the about 1 to 2 meter class. So, we feel very much that planetary defense is a global problem, and we want global participation, and that's the way we set up the conception of the mission. Just compare our target with deep impact, which was, I guess, on order of about 7 kilometers. You can see how tiny that we are relative to that, but very much within that representative threat. And so we view this as the first test of potentially many to come of a realistic scale for planetary defense. A high-level view of our objectives, obviously to do the kinetic deflection. You've heard a lot about models that we've been working with so far and gathering the data necessary to improve and do our best to validate those models with constraining the momentum enhancement. Understanding the concept of operations for this type of mission and how we might inform planning and policymakers when faced with a realistic scenario. And then there are many fundamental science objectives as well with the AIM collaboration to better understand the internal structure of NEOs and better validate those performance models. A little bit about our mission design. You're going to hear that we're set up to be a commercial ride share, so we have a very wide launch period of about 5 to 7 months. This is one case that I'm showing you here, and you can see that we get a commercial ride share to GTO. We'll remain in spiral around the Earth. After our Earth escape, we'll be on our way, and it's a relatively short mission of about 15 to 18 months. In our primary case, we have a flyby, which you heard one of the talks on that particular target. I believe it was yesterday, which we would very much like to do. And then I'll go a little bit more into the very important terminal phase of the mission. We have a single instrument on board, a visible narrow angle camera, that in this case you can think of it that we're using this almost in a missile defense scenario as a seeker, primarily for optical navigation and how it feeds into that system the data, as well as the data that goes into our autonomous navigation targeting system. So you can see after our spiral around the Earth, which is enabled by our solar electric propulsion system, and we go on to our escape and our cruise, we do a calibration with our flyby and a rehearsal to the extent that we can. It's not about 2 months that we'll get some course acquisition of our target, and not to about 3 hours where we'll actually be able to discern between the primary and the secondary, and then several hours where we actually lock into our target and do our final autonomous homing into our intercept. We're hitting at about 6 kilometers per second. And then afterwards, we have our impact assessment with our assets on the ground over several months to assess the deflection. And if AIM is on board, we'll do many additional observations for the crater and the scarring as well. Quick shot of our spacecraft. So we have a combined system of both solar electric propulsion and chemical propulsion. we're flying the ROSA arrays. You can see this, we call it the top hat here. That's for to protect the ion thruster from contamination as it's established within the secondary. I mentioned our visible imager. You're going to hear a little bit more about that. There's a lot of heritage with that. It's from the LARI system, which is the visible camera currently flying on New Horizons that have brought you those wonderful images of Pluto. We have a parallel technology program called NEXT-C, which is developing the xenon thrusters and the power processing unit, which we'll be getting as government furnished equipment, fully flight qualified, and DART is also the first test of that system. I mentioned about our commercial ride share. It gives us this opportunity in 2022, and in the event that we had a problem, we also have a subsequent opportunity in 2024, although we would lose the ability for radar as well as the 1 to 2 meter class small telescopes. But you can see we have this wide launch period. We intend to be ready in December of 2020 and could go all the way through May. In what we would if we went that long, we would give up our flyby. So we have a lot of flexibility for launch, which is very unusual for planetary missions, which have typically a very narrow launch window. A little bit about the organization. We've been funded to date under the NEO program with Lindley under the PDCO. We'll be moving over the Solar Systems Explorations program for Phase B for flight. In particular, I wanted to just show you the international aspect here and the communications networks that we have with our working groups and our interfaces with ESA. The DART investigation team, this is the U.S. side. We have members from all over the world participating. I won't go into the working groups. That'll be in the package and what their objectives are. To just wrap up on where we are, so we are on track to get our Phase B final letter of permission by the 1st of June, and our PDR will be next February, and we'll start major flight hardware development shortly thereafter. We have a series of international workshops. I'd like to invite you. Our next one is this June at APL, and you're all welcome to attend. That's advertised on the web, and you're going to hear more of that. Just right here, critical path is propulsion. And with that, I will wrap up. We have this wonderful opportunity, again, with the Didymos system to do our first test in planetary defense Kinetic-Impactor, as well as test out a lot of technologies. It's a very exciting mission, and we're pleased to be doing it. Thank you.
Thank you, Cheryl. A question for Cheryl? Anyone? Then if not, oh, yeah, one question there from Ed.
Can you talk a little bit about how you are thinking about various options depending upon what happens to AIDA?
Options in terms of realistic planetary defense systems?
No,
how it applies, or
meaning the DART mission itself. Would you, if AIDA can't make this launch opportunity but could make some other target later, would you consider delaying, for instance?
Well, I certainly can't speak for NASA, and they are the sponsor of this mission. But I think that, you know, the Didymos system gives us a second opportunity in 2024. In the event that that can be possible, sure, I think we would be open to exploring other binary systems. This first opportunity is pretty hard to beat. But yeah, we're constantly taking advantage of all the observation work that's being done, and we're still in a period, I'd say, that we have a certain amount of flexibility. We have a very tight cost cap with the vehicle. We're around $250 million. Anything that's extended, you know, always drives your cost up. So we're dedicated to try to stay within that amount. So right now we're headed to Didymos, and we'll see what happens.
Thank you again, and we'll move on to Andy with an update on the same project, right?
I think it's still.
All right, so I'm going to continue. Talk about the DART mission and what we hope to learn from it and how does it all work. So DART is the NASA Kinetic-Impactor, part of the AIDA mission, which is 2 missions, DART and AIM. I will talk about DART, and you will hear more about AIM in the following presentations. As we've already said, the target for DART is the moon of an asteroid binary. This is 65803 Didymos. The target is chosen Didymos because of a very close approach to Earth in October 2022. That is the time that the DART spacecraft will impact the moon of Didymos to cause a deflection of its orbit, and the objective is to deflect the binary orbit, to change the orbit of the moon around the binary, and then to measure that change with ground-based observations. I'll say a little bit more about what that's all about. And as also already been mentioned, the size of the target, which is 163 meter, that's our current estimate, based on the light curve observations of the size ratio between the two, the primary and the secondary. And as also, I believe, been mentioned earlier in this meeting, Didymos was well observed by radar during its previous close approach to Earth, which was in 2003. And because there is a good radar diameter, it's 780 meter, and a radar shape model, which is going to be refined. This is the initial analysis. Because we know the size, we have, it is a binary with a known period, and pole solution as well. The system mass, the total mass of the system is known fairly accurately. What we do not know, of course, is whether the densities of the two components are exactly the same or are they different. If we think that both objects formed from the same material, we would say, all right, probably we have the same composition, but there could well be differences in the structure. There could be macroporosity differences between the primary and secondary. Okay, so we don't know, we have some uncertainty of the density of the secondary versus the primary. Fine. And as also been mentioned, it's an S-type asteroid. So it's the same type of asteroid as Eros and Itokawa. Itokawa, the Hayabusa target. This chart you've seen an earlier version of already also. One of our key objectives is to measure the beta quantity, which is the ratio of the momentum, the push, the momentum transfer to the target, divided by the momentum that you brought in with the spacecraft. And they're not the same. Those two are not the same because of the ejecta, as is shown in the diagram. The ejecta carrying off momentum in the backward direction, and the recoil leads to enhanced momentum transfer. Also here, the chart shows if you assume an initial circular orbit for the binary, and that is consistent with our current observations. We know it's a low eccentricity orbit. If you assume it's actually circular, then it's become simple to calculate the period change. That's the blue curve, the eccentricity change, the red curve, and the inclination change. There's an inclination change because the incident trajectory of the DART spacecraft is not exactly in the orbital plane, and you can't avoid changing both the eccentricity and the period if you hit it in the back, or in the front, actually, in our case. And what I mean by front is that the impact, roughly speaking, is head-on into the orbital motion of the moon. Period change has already been mentioned, is a maximum of 7 minutes. We are actually targeting a decrease in the period. As I said, it's a head-on change, head-on impact, which will lower the period. All right. And the reason for that I can get into later. Well, talk to me afterwards. I wasn't going to talk about that. Okay. So this is a controlled experiment. It's very important. It'll be the first time where we will create a crater, and the AIM spacecraft will study a crater where we actually know what the impactor was, what direction it came from. We will also, from images obtained by DART and returned before the impact, know where it hit accurately. You will also be able to investigate the conditions, the geology of the impact site. So for instance, as we heard this morning, it makes a difference whether you hit a boulder, you hit next to a boulder. If there is any such thing, we will, in principle, know about it. So studying the target. Telescopic observations will actually determine the delta V, measure the change in the period, the orbital motion, comparing the period before and after the DART impact. That allows you to measure the delta V effectively that you imparted to your target. As I said, we have an idea already, and we hopefully, with the space of the mass of the target, and hopefully with the AIM spacecraft, we'll measure the mass of the target, and then also therefore determine the beta factor, actually measure it. One of the important outcomes of the DART mission will be, in fact, improved ability to predict the outcome of a kinetic impact on an asteroid. And so if we actually know what the physical property, if we learn something about, we characterize a target, a future target in advance, the information you learn from doing a controlled experiment will help you predict what the effect of a kinetic impactor would be. Okay. So we already mentioned the working groups. There are 5 of them. There's an impact simulation group. There's a remote sensing. So the telescopic observations we need, dynamical modeling of the asteroid, and then 2 more working groups about how to measure the properties, how to measure the outcomes of the impact and the ejecta dynamics. Okay, all right, the beta. Okay, let me just mention a few things. I know I could see I'm running out of time. The size of the crater that's expected depends a lot on the target properties, whether you assume it's porous or non-porous, strong, weak, etc. But we're talking diameters anywhere from several meters up to 20 meters or so. The beta values, you've heard a lot already about predictions, and the general range, values as low as close to 1, and values of 4, 5, 7. There are also laboratory experiments, which haven't heard. These are hypervelocity experiments in granite and pumice targets, and typically there's 2 papers here that are cited, and the beta of a little over 2 in both cases. It's very important to be able to measure the crater radius afterwards. That will help us a lot to determine, to understand the outcome. Okay, let me just go on. We also saw a lot about the impact simulation, so I won't talk about that. Beta values here, depending on the impact angle and depending on porosity. All right. The light curve observations, what these are plots of the brightness of the asteroid versus time. And what happens in a binary is that some of the light is blocked, either because one object blocks some sunlight from the other, or one object moves in front of the other. And because light is blocked, there's a dip in the brightness. And by measuring the timing of those dips, the period, that's how I would measure the period change. Okay, there have been observations in 2017. There's more planned in future apparitions, 2019, 2020, 2021, 2022. And in the 2017 campaign so far in February, already the mutual events have been seen. These are both mutual events in the system. And that work is actually in progress. I'm almost out of time. Let me just say a few more things. The dynamics modeling team is studying the natural changes in there's natural perturbations caused by something called Yorp effect, which is torque induced by thermal radiation. There's also solar perturbations, solar tides. We have to understand the natural effects to be able to pull them out of the observation, so that's being carefully modeled. We also understand that because both objects have irregular shapes, that there is important spin-orbit coupling, and that I assumed a very simple system, tidally locked, circular orbit, but that's obviously not necessarily so. There are librations of the secondary we expect at the 1 degree level, even before impact naturally. After the impact, it will be greatly excited because you've induced both an eccentricity in the orbit, and you have probably as well impacted off the center of mass, so you've induced a free libration. The libration amplitude after the impact is probably on the order of several degrees. That should be easily measurable, and we would hope that with a rendezvous spacecraft, you can measure the damping of that libration and then also estimate your tidal dissipation parameters. That would be a wonderful first experiment. All right, the camera's already been mentioned, some Pluto pictures. This is an Itokawa picture, but I wanted to mention that the best images are at the 10 centimeter per pixel level. These are in the last 5 seconds or so before the impact. Those will have to be returned to, the return is direct back to Earth. So anyway, and that's all I'm going to stop. We've already, these are the two, the DART mission website, the AIM mission website, and the workshop. Contact us if you're interested in coming. We want to invite you. We want to invite you all, but contact either Patrick Michel, who's sitting, sorry, or me.
Thank you. Thank you. I think we leave the questions offline. We ran out of time. And you have another talk on the same topic by Brian. So DART is not going away yet. Thank you.
Important things. Yeah, right.
Okay. All right.
That's correct. So this is your third straight talk on DART, but that's okay, because who could be bored with DART? Context of this study was that coming out of one of our early reviews, we had a question on, it's great, you're doing a lot of good stuff with DART to buy down the risk of future kinetic intercept missions, but is there anything you've missed? Is there anything else you should be doing on DART that you aren't already doing? And we thought, yeah, that's a pretty good question. So we went through a short exercise to say if we were actually going to do kinetic intercept, assuming DART as it was then designed had been successful, would we run into anything else along the way? So just again in context, this was done prior to the switch in the design from a all-chemical system to an electric propulsion system. So it'll look a little different than the pictures Cheryl showed you earlier. So our approach was, we didn't have time to do a kind of comprehensive look across, all sorts of orbits that we might intercept. Oh, I should also mention, before I leave, there was, of course, a team at APL, but Brent, pointing my laser pointer at you, Brent, I shouldn't do that. Brent was also very helpful and involved in this study, so if you have additional questions, point them to him. So what we did was we took a couple of orbits. We had the hypothetical PDC from the last one and Bennu as examples of orbits which one might want to do an intercept against. And we did a design saying we'll take what we have from DART and we'll build it up to a mass that would be relevant for actually performing an intercept. And then in the process of getting ready for this, I should put recently in quotes now too, because obviously this was detected a little while ago, but a new asteroid popped up near the Earth and it was just like, okay, well I might as well study that one. So we designed to these two and then we studied whether it would work on the third case, and the answer is it worked pretty well, and I'll show you that in a moment. So this is the old version of DART before we went to electric propulsion. It was a very small spacecraft, about a little under 300 kilograms. And obviously we need more mass than 300 kilograms to do any sort of deflection against a large object coming in. But so we had the changes to the structure because we had to support a lot more mass. And because the orbit wasn't quite as benign around the sun, we had to go a little closer to the sun than we do on DART. We had to do some other things thermally. The main one was adding louvers in order to accommodate the lower solar distances. But for the most part, there weren't any really significant changes from what you might expect other than just going to a slightly different orbit. One of the things that was very interesting was we were wondering whether the autonomous navigation and the GNC would require any significant change. It turned out that when we scaled up to the larger spacecraft, we had to scale up the thruster size, but the end result were the accelerations were more or less the same. So there really wasn't much difference at all in how the navigation would perform. So when we did what we did was we evaluated how much deflection you would get for what size object you could deflect with the maximum mass on a couple different launch vehicles, the ones that we would typically use in the US. We assumed just a spherical body for this purpose, so it's not perfect, and roughly a 10-year deflection from deflection to whenever the closest approach would be. And then we just plotted for different numbers of impactors what size body you could do, and lo and behold, it's in kind of the range and maybe even a little better than what you might normally expect for a kinetic intercept. I should add that since then we have a new PDC and a new orbit, and we did go back and look at that, and again, Brent was helpful and some of our folks worked on it. And in that case, you probably want to go a little bit closer to the sun or a little bit further away than what we spec this for, but in general it held. I'll talk about that, I think, on the next slide. I should say that in all these cases, the C3 and the required delta V were very, very similar, so there isn't a huge difference in the delivered mass to the asteroid. The main difference in the deflection performance just has to do with the relative velocity at impact. So as we said, we designed that one to 0.8 to 1.2. Some of Brent's work and our work for this current PDC said you probably want to look down to 0.7. Brent would like to go to 0.5, but even 0.7 is very driving from a thermal design perspective for the spacecraft, so I would have pushed back on that if I were the engineer involved. We accepted a little bit lower data rates, but we were still getting high enough data rate to validate, to understand where we were hitting. I mentioned the issue with the thrusters. Visible imaging was a question we had going in. We were wondering whether, it would have been better in theory for DART to use IR imaging because that would get you a larger range of solar phase angles which you could encounter, but everything that we looked at was pretty well managed by visible. And the other piece is that despite the range of orbit of heliocentric range that we had to consider, the impacts were typically not at the largest possible solar range, so we weren't dealing with the minimum solar illumination of the target. So now, and I'm running out of time, and this is the interesting part, assuming we've done DART, how can we turn around a kinetic intercept mission rapidly? Well, you can always go scrounge up all the components and build something, but there are a lot of spacecraft that are being built all the time, and the most common ones are, of course, the geosynchronous communications spacecraft. So we had the question of, would it make sense to take some pieces of DART and go find whatever was on the INT floor and see what you could patch together? And it seems like this is possibly a reasonable approach. There's some questions you have, especially if you have to go to 0.7 AU. You're going to have to change the thermal systems a little bit more than we would have liked. But the proposed approach was to take the DART avionics and imager. The avionics now become a data processing unit that just attach on to the GEO spacecraft in place of their payload. We were proposing bringing a radio and antenna. They have a lot of communication, but they don't typically use DSN, so we thought it would be easier for them if we just brought that piece of the package along. We could probably get a long way on this with a pretty short study, just some relatively cheap studies, talking to some of the ComSat providers and identifying the interfaces and figuring out what the best way to do this. We also have to bulk up the mass. We were thinking we'd do that mostly at the SEP system. where it doesn't impact the rest of the structure, but there's still questions about maintaining torque authority as you go forward. We also did a very quick assessment, and I'm going to be talking about it very quickly given the time I have left. We looked mostly at ULA launch vehicles because that was the easiest to get information about, but we thought this would be representative, at least to identify if there are issues with doing a campaign of kinetic interceptors, as we are discussing in this current exercise at the conference. Trying to launch an Atlas more than monthly would start to become challenging without doing some prior work. If you're trying to launch Delta IV Heavies, trying to launch them more than every 1.5 months is going to be challenging. And another problem is that you're probably going to want a 5-meter fairing for these larger spacecraft. There are not that many 5-meter fairings prepared, so if you're talking a couple of kinetic interceptors, that's fine. If you need 6, now you're starting to push the envelope a little bit. We did not assess SpaceX and foreign launch capabilities, so that's clearly something that we need to do going forward to get a better sense of whether this is really an issue. So what sorts of things could we be doing based on this look? Well, obviously, we should execute DART, and I'm not an unbiased observer on this, so I'll stop there. We should be trying, though, to understand how can we shorten the timelines from the moment we learn something in order till the point where we can launch those kinetic interceptors. We should do a little bit more work on what would be involved in integrating with the geocomsats and assessing the launch vehicles. And I will stop there.
Any question?
What mass did you assume for the impactors? Because you indicated you had a series of masses you were looking at.
So the masses for the impactors were, we assumed we would put ballast mass on the spacecraft up to the limit of what the launch vehicle could deliver to the required C3. And we would scale up the propulsion tank in order to get the delta V we needed. That was for the DART, the specifically designed for the kinetic impactor case. For the geocomsat case, we didn't go to that level of detail. We would have to assess that a little bit more. That's getting more complicated as the comsat world is moving more and more towards hybrid electric propulsion and chemical solutions. We have to assess timelines. If you're going to have to swap out the tank, then that becomes a limiting issue and would probably prevent us using them that way. So we would run into a limit on the impactor mass short of what the launch vehicles could deliver. But for the independently defined one, we had the flexibility just to scale it up to whatever mass the launch vehicle could handle.
All right. We have to move to the next speaker. Thank you very much. Next speaker is Ian Carnelli of European Space Agency, who's going to talk about AIM, minimum system designed to support planetary defense demonstration.
Yes, good morning. So as you can imagine, this is the talk I'm going to give today is quite different from what I was hoping to give today. I was hoping I would announce this community a mission, but unfortunately we're not quite there yet. So as you know, in December we went to the ministerial conference. This is our highest level body in ESA, where we decide every 3 years the missions that our agency is going to do. And well, there's a few. So what happened, for those who have not heard the story, we were asking for 105 million euros. That was to cover the industrial cost. We got to 70, but we could not get the remaining 35. So we had to withdraw this proposal from the table. And okay, meaning that some of the funding are still there. We cannot engage them until we don't have the full funding. But it also means that there are a number of countries in Europe that are interested in this type of activities. On the other side, it also shows that planetary defense is not to a level of maturity in Europe to have enough backing to implement a mitigation mission, a mitigation demonstration mission. So my first pledge is we need to grow in Europe as a community to support this type of activities. Clearly, the space stations and Ariane 6 developments and ExoMars and other programs are much bigger. I must also confess, I have a lot of lessons learned, but one of them is also that the asteroid community is a bit spread, although there are not many asteroid missions in Europe, I must say, in the near future, or actually in the future. The backing of the community itself with regard to an asteroid deflection demonstration mission was not as strong as one would expect. And that's because they don't feel engaged. Although, as we have showed, there's a lot of science involved also as a byproduct of such a mission. So there are a few things that I think we need to work as a community to make this happen. On the positive note, what you see in the picture is European ministers, so the highest level of decision makers for space activities. And on the positive note, many of them had very high speeches with regard to the need of having a mission like AIDA and the importance to have AIDA implemented. So I think we have a real opportunity to make this happen. I think we also set a precedent, and for those who know about the Don Quixote studies, I think we made, I think I was involved from the very beginning, I think we've made a very long journey, and we are really close, so we keep pushing. This is the AIDA mission that we presented at the ministerial conference, and compared to Rosetta, so it shows a little bit the change in spirit and mindset of doing planetary exploration and small body exploration. Of course, they're completely different missions, but what it says that even Rosetta took a few years from when it was proposed to when it was launched. And I hope that if we scale it by the mass, probably we take 3 times less to implement it. So this is what we're working on. So what did we do? After the ministerial, basically, we had many countries that asked us to find a solution and implement the mission. So with the money we had, we tried to basically simplify the mission. I must say it was quite ambitious. We had a lender, we had optical communication, we had many things. So we had to scale down. And the first, let's say, the main drivers were indeed the optical comm and the lender. So we reduced the mission scenario. I won't go through all of it, but basically the main difference is that by just having a CubeSat and a camera, we can achieve, and Patrick will go into that, all of the mission objectives related to asteroid deflection test. But we can avoid all the complications of getting closer than 10 kilometers, and let's say 12 kilometers is kind of a technology thresholds in the simplicity of the mission and in the cost of operations. There are a lot of implications into the cost of the mission if you go closer than 12 kilometers. For the rest is the similar, and of course, the other main change is that we missed the 2020 launch date opportunity. It was a tight schedule, we knew it. We had prepared for it, but we had, in order to achieve it, we had to have the funding in December. So we're now currently targeting the next launch opportunity. So this is the spacecraft, which basically at the moment has 2 navigation cameras, which we have in storage. These are the cameras that were used on Dawn, and there are 2 flight spares and quite a number of qualification models that we are actually using for test. And we also have the support of Finland for the Aspect CubeSat, which is a very important element of the mission because it's de-risking the observations during in close proximity by sending a silver spacecraft. There are other payloads that are supported, but let's say are in standby. One is a hyperspectral camera with planetary sources and an altimeter with Polish and Portuguese companies. These will be implemented if AIM gets the the remaining funding. This is the current layout. It's not a very beautiful spacecraft. Personally, I think we should have 2 solar wings, but the message is quite simple, very small. The mass, we got basically to 130 kilograms below the mass target. So we have plenty of margin at the moment. What this says is that in the current design, we have 40 kilograms that we can allocate to additional payload if needed, and then around 100 kilograms for the impact that this payload would have at system level. We finished the spacecraft design. We have completed the GNC testing of the cameras. Of course, these cameras were designed for dawn, so we had to do a lot of work to make sure they would be fit for the AIM scenario. And our aspect team is currently doing a detailed design of the aspect CubeSat. I said we simplified the mission. I have to actually thank Holger Sierks for the cameras that he has given to us. One of the things is that we moved from completely autonomous optical navigation to only landmark tracking. And the difference might not seem much, but in reality it's a huge implication on cost and operations, meaning that what we're going to do now in the baseline is only to use landmarks to do autonomous tracking, but not autonomous navigation. The navigations is planned by using the expertise of our operations team in the Rosetta mission and done fully on ground. It's actually cheaper than doing a fully autonomous spacecraft because of the level of testing it needs to qualify operationally the autonomy. So these are the type of trajectories we would fly around Didymos. For those who have followed Rosetta, they follow the similar logic. You need to do this kind of pyramid or quadrilateral arcs to do orbital determination and plan for the maneuvers. The GNC results show that we get an accuracy of about 20 meters from our navigation in position. Now, just to conclude, as you heard on Monday, our Director General, so it's the same level of the NASA administrator, has said very clearly that planetary defense, he's fully convinced that planetary defense is a need. We need to work on that. So the plan is to present it to the Ministerial of 19. And I think we're going to use this political support to make sure that this is brought to the right level of attention and is given priority at the next ministerial. So this is a quite strong message from him. We're also trying to extend the international collaboration. We had proposals from other countries, and this is actually going to, we'll take that into account. And I'll conclude. So stay tuned. I want just to thank the team. I don't have everybody, I'm sorry for that, but it's been, I think, a fantastic ride over the last 5 years. I want to thank everybody who has contributed to that. And the message is, yes, don't give up, we keep pushing. And I think we're gonna make it. Thanks a lot.
Probably. Okay, we continue now with Patrick Michel, who's talking about him as well.
Yeah, I'm going to just rapidly recall the objective of the new scheme. If I can. Yes. Okay. Okay, so just to remind you, the target is Didymos. So you see it close to Burj Khalifa, which is about the same height as the primary. But the target is a secondary, and as we said, this is the right size, I would say, for a planetary defense demonstration, because this is a kind of size that we can care about. Larger size, the frequency is much lower, the impact frequency, and anyway, Kinetic-Impactor will only work up to a few hundred meters in size, and very lower size than we don't really need to care because the impact is so local that the probability that it goes over a populated area is very small. So between 50 and a few hundred meters is, I think, the right size for this kind of approach. And this is also good because in the context of other space missions, we'll have OSIRIS-REx and Hayabusa 2. And as you can see, Hayabusa 2 will go to 850 meter wide, I think now it is. Asteroid, Bennu 500 meter. And so if we have AIM, then we go 3 times less wide than Bennu. So we go smaller and smaller. And that also allows us to understand how the processes that act on asteroids scale with gravity. We still have a very poor knowledge of the dynamics of the regolith, in particular in a low gravity environment. And so if we can see how it works on 3 different kind of masses, that will be very interesting. So this is a setup that we have for this mission, as we have seen already. So we have ESA, we have NASA, we have 2 team leaders here, and we have now these payloads, which are basically a framing camera and a CubeSat aspect. So the concept is to arrive at the... how do I cut the sound? It's in French, sorry, but... okay, so whatever. So basically what we want is to arrive at Didymos, and then we want to measure the mass, because of course if you want to characterize beta, you need an information on the mass. So either you have an estimate, or with AIM you can directly measure it. Then once this is done, we will deploy the CubeSat aspect that will observe basically spectrally the Didymoon, and then we'll also observe hopefully what happens during the impact. So AIM will go away, and then DART will arrive, and then make the impact. That's the original plan. And we will observe then the plume, and finally the crater size. So this is very important, of course, for a planetary defense demonstration, but also it will allow us to really understand how the impact process works at asteroid scale. And this is important because, as you know, collisions played a fundamental role during the whole solar system history, starting from the initial phase where collisions ended up in agglomeration and planet formation. Then we had the era of giant impact with the moon formation. And then we are now in the era of asteroid collisional disruption. And so far, all the collisional evolution models rely on sort of ad hoc parameters to decide what happens when 2 bodies collide together, which are based on laboratory experiments, scaling laws, but we don't have yet a real documented experiment at this scale. So it would be important to have it not only for planetary defense, but also for many other topics in planetary science. So in order to do so, we have these framing cameras by Holger Sirks, which Jan presented, and we have also this CubeSat. And Thomas, oh, by the way we measure the mass is that we'll measure the wobble, basically, which is due to the displacement of the center of mass in a binary system. And then we'll have the CubeSat, and Thomas Kohut is here, and you can talk with him about the specification, but basically we'll have a visible near-infrared imaging spectrometer. We can study space weathering, shock experiment, and the plume observation out of the impact. And something interesting also will be to understand how the dynamics of the ejecta after the impact. In particular, in a binary environment, of course, the dynamics may be quite complex because you have a sort of a 3-body problem. So that could be very interesting to study. So basically, the objective, I mean, the outcome of the AIM mission, even the reduced one, would be to have the first images of the smallest asteroid ever visited, because Itokawa was 320 meters in size, the other ones are larger. So we don't have yet a direct image of a 150-meter body. So we don't really know what kind of structure or regolith properties there is on this surface. That will also, as I said, allow us to understand physical, conventional properties and geographical processes in low-gravity environments. And of course, with that, we'll have the first documented impact experiment. So the initial condition and the outcome, crater size, etc. That will allow us to validate the numerical simulation at this scale, as we have done in laboratory. And of course, as I said, it will provide constraints to evolution models. So in order for this to happen, as Jan said, we need the support of the community. And I'm talking to the European colleagues. Remember that there is no small body mission anymore in any program at ESA. at least until 2030. If the M5 class mission, the science mission, is a small body mission, the launch will be a minimum 2030. So if we want to keep, the momentum, and we know when a space mission is selected how it generates a lot of things, good things in a community, then we need to fight for it. And I can say we still have the engagement of the public and the media that keep asking about this mission. They keep thinking that it will happen. So we need to be able to answer positively to these people, the journalists and the young people, because this is a source of inspiration. And this was already demonstrated with Hayabusa, which was actually the topic of 3 movies. So hopefully one time we'll be able to present the movie of AIDA after it was done. Thank you.
Well, we have time for questions, so any question?
Patrick, you mentioned 2 scenarios. One is the standalone, and next with DART. What is your opinion? Which option is more realistic at the moment?
The option I want is both.
Yes, sure.
What is realistic in the space business is only what you know it when it happened. So I would say for the moment we count on this international cooperation.
So you still are not still guaranteed that some ministerial meeting or something else will not cut further the project?
We don't know. I mean, we fight for it. And even though the last ministerial was negative, as we said, the DG of ESA still wants to push for it. He wants to present it as a minister.
Exactly my next question, short one, that relates to what are forms of support from community, not just for public, but also for professional community. We have signed this appeal from Mr. Borden, but I think that's not enough. But what do you think that should we organize some kind of campaign? I don't know what will be considered by ESA as an argument?
You mean what kind of campaign we should do in order to make it happen? That's the question. We have to convince the member states. We have a few member states who are highly motivated to do it, in particular Luxembourg, for instance, who is really pushing for it. But during the ministerials, every member state has its own priority. And as long as it is not seen as a priority by enough member states, then it won't happen. So we have time to convince, and that's the role of the community, to talk with our delegates and to explain why it is important and time to do it. And so that's the only thing we can do. And I think we have a good rationale for it. Also, it brings a lot of visibility. So you need to explain all of these things to the delegates. And for this, it's not only me, it has to come from the different experts in different member states that should talk with their delegates. That's how it works. The problem with ISA, you have 22 countries and you have to have a common agreement.
And related to that, what are the competing concepts in Europe?
There is no competing concept.
So it just wasn't funded.
It just wasn't funded. It's, for me, still ununderstandable, but that's how it is. It's we cannot understand.
Let's focus on space, I guess.
A good thing also is to have the support of also countries outside of Europe. I mean, it's more convincing when even in Europe we feel that there is an international pressure.
Thank you very much, Patrick.
Okay, thank you.
Next speaker is Dan Mazanek of NASA, who's going to talk about the enhanced gravity tractor applied on the hypothetical 2017 PDC using the ARM vehicle.
Thank you, Marco. All right, good morning. Thank you, or actually, yeah, it's still morning. Thanks for having me here. I'd like to acknowledge my colleagues David Reeves and Paul Abel, who are here in the audience. So if you have any questions, they're also available to talk to during breaks. And Haijun Shen and Min Q, who helped with the analysis here. I'm going to talk about the enhanced gravity tractor that we were proposing to do under the ARM mission and how a derived vehicle from that mission could be used for 2017 PDC. And let's see. Make sure. Am I on? Sorry about that. Try it now. Okay, there we go. All right. First, just a little background on the Asteroid Redirect mission. Again, for anybody that's not familiar with it, the concept had three basic phases. The identification phase, where we use assets on the ground and space-based to identify targets. The robotic redirect mission, which was basically a solar electric propulsion system to go out to a near-Earth asteroid, several hundred-meter class, and return a boulder from that asteroid back to cislunar space, where the crew members would be launched to explore the return boulder material in near-Earth space. Just an update in terms of not being funded, the Asteroid Redirect mission was not in the President's FY18 budget blueprint, and at this point, the current concept in its current form is not moving forward. Some of the technologies and capabilities from that mission are continuing, for example, the SEP system and some of the other aspects. Obviously, we are going to be doing some crewed exploration, but at this point, the Asteroid Redirect mission won't be going forward in its form. Now, that being said, the concept, and we've been working on this for several years, is still a good one in my opinion. Just to give a brief overview, focusing on the robotic segment, we first of all traverse out to the asteroid. We have a period of approach and characterization, the boulder collection, and then we demonstrate the enhanced gravity tractor. And this would have been the first demonstration on this mission of that technique, where we utilize the boulder in addition to the mass of the spacecraft in order to provide a much more significant gravitational attraction between the two. And again, you can see the rest of the mission, the inbound crews and the crew operations. But I'm going to focus here on the enhanced gravity tractor portion of it. We did a lot of work during ARM looking at different operational modes. I won't go into detail here, but we traded off the halo orbit versus the inline. And we found that for the ARM mission itself, that the inline offered some advantages in the uncertainties and the constraints of the mission. However, you can see the strengths and weaknesses, and again, all these charts are in the presentation package, so you can take a look at them, and if you have any questions, be glad to answer them. There are several strengths of the halo orbit in terms of its ability to take advantage of the higher mass that you collect during the mission for the enhanced gravity tractor portion. One thing to talk about in terms of the enhanced gravity tractor, yeah, I thought that was my watch for a second, is just the power of multiplication. The gravitational attraction force from the traditional gravity tractor is limited by the mass of the spacecraft, or whatever mass you bring out to the target. And this means the deflection efforts can take many decades. It's a very elegant approach, but it takes time. And the spin that we put on it here as part of the Asteroid Redirect mission is, what if we, as we were in ARM, could amplify or increase the mass of the spacecraft? And you can see that the base equation allows you to greatly enhance that. And the only, as long as the spacecraft has sufficient thrust and propellant capability, the force is limited by the amount that you can collect. So for example, if you take a 1,000,000-ton asteroid, which is about the potentially hazardous size of 140 meters for 2 grams per cc, and a 10-ton spacecraft, you get about a force that's proportional about 10 million tons. If you can collect 990 tons, basically turning that 10-ton spacecraft into a 1,000-ton spacecraft, you can increase that gravitational force by 2 orders of magnitude. So that is the power, because you're only taking a little bit of mass away from the main asteroid, but you're greatly amplifying the other mass that's in that equation. Some of the pros and cons of the enhanced gravity tractor versus the standard. Again, it's a very slow push technique, so you need time, but that has its benefits in terms of the very low forces that are imparted. I won't go through all of them, but one of the biggest cons, like I mentioned, is the long thrust lead times for the standard gravity tractor. The biggest con of the enhanced gravity tractor is the fact that you have to collect the mass. And we've been kind of going at it the approach that ARM would have demonstrated this as a first demonstration, but it's really reliant on the commercial mining industry and becoming a spacefaring species that would allow this type of approach to be enabled. If we can understand and be very proficient in harvesting mass from asteroids, we thought that this approach would fit very well in a long-term plan. So here's 27 PDC overview. It's in the packet. We've already talked about that. A couple of the deflection assumptions. We looked at 100 to 250 meter diameter with bulk densities of 2 and 4 grams per cc. The 4 grams is in the backup due to time. We went with the same thruster configuration that John Brophy talked about earlier with the 7,000 second ISP. This is actually higher than the ARM robotic spacecraft, which means there's less thrust, but it's more fuel efficient. And you can see the power levels that we assumed from 40 kilowatts up to 300 kilowatts and the thrust available at 1 AU. Of course, you have to collect the mass, and we utilize the halo method and full thrust capability to deflect the asteroid. And you can see that table in terms of the mass that has to be collected for 100 to 250 meters. You're talking tens of tons up to hundreds of tons for the 300 kilowatt system. And again, as the asteroid gets more massive, you actually collect a little bit less because you have the higher force to maintain. And we utilized the 2017 ephemeris and B-plane data that Paul Chodas provided for doing this analysis. So some of the results for the 40 kilowatt system, and just to give you the lay of the land here, we went ahead and pulled this out to 10 years before impact time. So that would be basically you have to be on station immediately, which is obviously not feasible. So we focused more down at the very optimistic side of about 7 years and looking at that forward. So this is time before impact, and this is the zeta deflection in the B-plane with 1 Earth radii being our kind of our benchmark. Now, of course, it could be less, again, as we get more information about the actual impact location, but we use that 1 as kind of the benchmark for deflection here. So what we found is for the 40 kilowatt, and you can see that the 100 meter is here in blue, all the way down to the 250 meter in 2 grams per cc, but the 40 kilowatt can deflect PDC size asteroids up to about 100 meters in less than 3.5 years. So you're talking about somewhere here. And so the ARM class spacecraft with a little bit higher ISP could deflect asteroids up to about 150 meters in size range, which doesn't cover the full range. So we looked at the 150 kilowatt, which could go up to 200 meter diameter in less than 6 years. And then if you look at the 300 kilowatt, you could deflect up to the 250 meter diameter in less than 6 years, which you can see here. Now, that still means various aspects of development and deployment have to be addressed. But one of the reasons that we also went with the higher ISP was that it resulted in reasonable propellant quantities. You can see here as at the 6-year level, you're talking somewhere between, say, 1,000 and 4,000 metric tons of propellant, depending on the case. Now, this does not include the propellant required to transport the EGT system to the asteroid. That was added in the next phase of the analysis during the trajectory analysis. So we utilized NASA's Copernicus software, and we also utilized a departure stage from the Earth vicinity along with the SEP to be used during transit to the asteroid, giving an additional 5% tankage for propellant consumed during there. We utilized the 7-year propellant estimate that was derived from the EGT operations. We didn't optimize for shorter ones. We just went ahead and used that. This is kind of a first-level parametric study. And you can kind of see the wet mass and the dry mass of the vehicles that would be needed for the different cases. We assumed a chemical propulsion stage, leaving either from low Earth orbit or high Earth orbit. And you can see this is, in the back there's the trajectory diagrams, but these are the summations of the departure opportunities. And you can see for the 40 kilowatt class, you basically have to leave right now. So the time to get to the asteroid requires an immediate departure. The mass requirements in terms of stages, about a 20 to 30 ton stage from LEO and a 4 to 7 ton stage from HEO are pretty reasonable there. The 150 kilowatt class, you have more opportunities. You have opportunities now in 18 and then finally in 2020 to get there in time to deflect the asteroid. And the departure stage requirements start to go up, but they're still pretty reasonable. The 300 kilowatt is a more massive system, so it does require the largest departure stage, but you're still talking about a 60 ton from LEO and about a 10 ton from HEO with the same sorts of times for arrival. So in summary, and there's some more data in the package, folks feel free to look at it, this case study has demonstrated that hypothetical asteroid 27 PDC can be effectively deflected or used to deflect hazardous asteroids in a period of years rather than decades. PDC is still a very short duration, short warning time case, but we do see that we can do that. And the initial trajectory analysis shows that these systems can be delivered in a timely manner using reasonably sized chemical propulsion stages. So in closing, I'd just like to make a couple remarks, and the first one is that multiple techniques should definitely be considered in a systems of systems approach. You know, when we go out to fix something in the field, we don't just bring one tool, and Lindley's fond of the toolbox analogy for planetary defense. I'm fond of bringing the whole toolbox. If we can bring multiple approaches, for example, a Kinetic-Impactor could be paired with the enhanced gravity tractor in some way, shape, or form, potentially providing trim capability after a kinetic impact. And it also, the deficiency of the kinetic impact is we may not know a priori if we're going to disrupt it. So that can be kind of a real-time decision that can be made. The other aspect is on-orbit resources and expertise in interacting with asteroids are critical to responding in a timely manner. Eliminating the development and launch costs, or launch time, excuse me, is critical. So if we have capabilities on orbit that we can utilize, and we talked about this during the exercise, repurposing assets was one of the first questions. What can we use that we already have? And finally, I'd just like to say that the planetary defense and asteroid mining communities, I think, are closely linked, maybe inextricably. I think the PD community should work with the asteroid community, mining community, as it develops. And the fruition of that capability to be proficient in asteroid mining is really enabling for the EGT option. So thanks.
We have time for a couple of questions. No questions? Okay, thank you very much. The last speaker of this morning session is Anastassios Petropoulos, who's going to talk about asteroid deflection campaign design for scenarios with decade-long warning times.
Thank you, Marco. Thank you, Marco, once again. Good afternoon. I'd like to acknowledge my co-defenders, Frank Leipert, Javier Roa, and Paul Chodis. Here he's wearing his defender hat rather than the threat master hat that he's been doing for us so far. So this will be a bit of a walk in the park of orbit mechanics. So it's something that we haven't really focused on very much yet in the conference, but I think it will dovetail nicely with the talks that we have in the afternoon of today from Brent and Claudio and a couple of others. So we are looking at characterization and deflection approaches for our hypothetical threat, the 2017 PDC. We're using solar electric propulsion here because we feel that it typically gives much higher impact and arrival mass than chemical propulsion, and it also gives you flexibility in the launch period. You can launch over months typically versus weeks for chemical typically for a given mission. It's been demonstrated in deep space. Dawn has demonstrated it. Hayabusa has demonstrated it twice. Procyon has demonstrated it. And of course, Deep Space One has demonstrated it in deep space. I'm talking about beyond the Earth-Moon environment. So for characterization, I'm talking about a flyby and or rendezvous mission. And for deflection, we're talking about a kinetic impactor, although the rendezvous mission might also be used to carry a nuclear payload, as the breakout sessions I've been talking about. The launch dates, I should mention, about 2 years or more after detection, 2 years, of course, being on the sporty side, depending on what people or the community decides to do. Okay, so some speed considerations and impact geometry. The optical navigation has to be at a sun phase angle of less than about 120 degrees. 90 degrees or less is preferable. The impact speed of up to about 20 kilometers per second should be achievable, even for an object of 100-meter diameter. The question of disrupting the asteroid has been discussed severally by several talks today. If we suppose that the cap, the upper limit on the delta V imparted to the asteroid is proportional to the escape velocity at the surface of the asteroid, and if we further assume that the delta V you impart to the asteroid is related to the approach velocity and the beta factor, of course, you end up with this relationship between the upper limit on the delta V imparted and the delta V you actually impart. You see a dependence of d to the power 4, whereas the density is only a weak determinator of this. So the flyby mission will characterize d very easily, and I think that's the most important thing to do early on. Okay, so now we get into the orbit mechanics per se. If we do an early launch, a July 2019 launch, that's our 1% probability of impact date. 2 years from our 1% probability impact date, we would depart from the Earth here with low thrust. The launch V infinity is 6.56 kilometers per second, so a C3 of about 40. We're changing our orbit shape with the low thrust and impacting here at, rendezvousing here in late 2020. So that's a relatively quick characterization mission, and you have an asset in place for subsequent kinetic impactors. If you launch early again, but want to arrive earlier, you can still do that, but the arrival mass at the asteroid will be much smaller, and you have to launch with a relatively high V infinity of 10 kilometers per second. And if that sounds high, New Horizons launched with a C3 of 160 or 170, so this is a C3 of 10. I should mention that all of these, I put the assumptions up here. These are for 3 Next engines, 25 kilowatt arrays, and an Atlas V class launch vehicle. If you do an even earlier launch because you are so inclined, you can arrive with considerably more mass at the asteroid. That might be an option for a nuclear scenario. You can also launch yet earlier and arrive earlier. The advantage of going very close to the sun is that you change your energy much more efficiently at that point. This is about 0.5 or 0.6 AU, and that's a little bit sporty, but not impossible by any means. After all, we are operating around Mercury already. The other option for doing a late launch is launching in 2020. This is the option that Paul talked about already. Again, launching with a high C3 of 100 on an Atlas family and arriving in 2023, just a little bit after aphelion. There could also be a chemical counterpart to this mission, because you're not doing very much low thrust in here. What the chemical buys you here is a spread of launch dates. the corresponding, I show this here, and the impactor I showed in the characterization slides because it's related to this trajectory. So this same trajectory can be changed slightly, launch a little bit earlier, and send your apoapsis with low thrust very high, and come here and with a higher speed than the asteroid, hit the asteroid at its periapsis, and get a deflection of 10,000 kilometers for a 100-meter porous rock asteroid, a beta of 2. This one is also an interesting one because you launch from the Earth, you launch early in 2019, July of 2019. You do a flyby of the asteroid early in its orbit before perihelion, and you come back and rendezvous with it later. So this buys you the diameter early on and some other characteristics, perhaps the shape, perhaps some spectroscopic information, and then you can come back and observe the impact from a rendezvous state. Okay, now we get to the deflection aspects of the talk. The first thing we did was we looked at direct SEP trajectories. That means without any gravity assists. And the delta V is assumed to be in the anti-velocity direction. Let me show you the assumptions here. So this is a vector V here, and I think this is important to note because there were other talks earlier in the conference about obliqueness of impact and what that means. So an oblique impact here would give you a delta V in a bit of a wrong direction, so you get some losses. So effectively, you can think of beta becoming less than 1, which of course it can't be, but effectively it's less than 1 because you're not getting the momentum transfer in the direction that you want. So we looked at a large variety of launch vehicles and power levels and engine configurations. I'll just give you one example here. This is a trajectory where you would launch from the Earth and get into an orbit that's smaller than the Earth's orbit and position yourself in front of the asteroid near its perihelion. So here we're arriving or impacting with a speed relative to the asteroid of 15 kilometers per second. And if you look at the entire map of launch dates versus arrival dates for these kinds of missions, similar to the one I just showed, you can see here that all of these deflections are in the negative zeta direction, down to about minus 9,000 kilometers, and up to 0, no positive deflections here. But really, the SEP buys you this full color spectrum of options here. You can launch and arrive whenever you like in this space. There's also a last-ditch effort where you depart the Earth in 2026 and you arrive in 2017 or impact in 2017, but the velocity is very, very high. So you have to deal with disruption. But assuming you don't have any disruption, here's the deflection that you would get in the plus zeta. So just to summarize the results of the direct SEP missions, you have launches as early as 2020 with a deflection in the plus zeta direction. That's the one mission we showed with plus zeta deflection. And more than 1 Earth radius for all the other options that we looked at. 3 next engines, 25 kilowatts, 2 next engines, 20 kilowatts, and so on down the line. And also for a late launch, a 2023 launch, you can still get a fair deflection with 3 next engines and 25 kilowatts. I'd like to point out one interesting point here, that with an SLS-1B, you can still deflect almost 9,000 kilograms, even if it's an iron asteroid, a cannonball. The flip question that you can ask is, let's give ourselves some margin. We want to deflect 4 Earth radii in the plus zeta direction. In the negative zeta direction, typo. How large can the asteroid be and you still deflect? Okay, lastly, I know I have just a very short time left, but not many slides here. The SEP with gravity assists, we did a broad search based on logarithmic spirals, some of which are pictured here. We filtered those results and optimized them using our local trajectory optimizer. And we have a tabulated list of cases here. I'd like to point out that the Earth-Venus case is probably one of the best ones, an Earth-Venus flyby, deflecting for a 250-meter asteroid, 9,127 kilometers. Another interesting question to ask is, what is the biggest deflection that you could have? And so you take your best trajectory, which is the Earth-Venus trajectory. You take your heaviest launch vehicle, SLS Block 2, give it a lot of power, a lot of engines. The Hermes are the ARM engines. You assume a beta of 1 that's pessimistic, and you get a trajectory that looks something like this, quite doable. You launch from the Earth in early 2020, so not too early, not too late. And here's a deflection map for that case for various asteroid diameters, 100 through 250, and all the way to a density of iron on the x-axis here. So the 4 Earth radii deflection line here is here, and this is in the minus zeta direction. So in conclusion, I'd like to point out that we have large asteroids can be a challenge. They likely will require multiple launches, multiple impacts for a significant deflection. For a 250-meter iron object, you would need multiple launches even with an SLS launch system. For the smaller objects, you can get away with a single mission on Atlas V 551, but you may need multiple smaller missions if disruption is a concern, which your flyby mission and rendezvous mission would tell you. Some room to improve. Deflection was not directly maximized in our software here, and we need a better understanding of the disruption limit. So with a better understanding, we can get better bounding boxes on our results. And with maximizing the deflection directly, we can get more realistic aspects. It was optimized by hand really right now. I would like to close with a movie, if I may.
Yes, you have time. Do you know how to open it? Yeah, make it work for you. Okay, clean slate. So I wanted to show this movie because it really exemplifies what multiple actors acting in concert can do when they're working towards a common goal. And it's sort of a cosmic dance, and I hope that if we are ever faced with a real threat like this, we would, as a world of nations, come together and try and ward something off. So this movie shows the trajectories of the bodies and so these are missions that are leaving from the Earth. All these different colored lines are missions leaving from the Earth, doing different gravity assists, all on their way to impact this the asteroid on this orbit here, on its orbit. So they're all doing their own, following their own path, but really having a common goal of impacting the asteroid. So you see the lines terminate here, and one by one the lines terminate on the asteroid to achieve a common goal of deflecting it.
With that, I'd like to take any questions. Thank you.
Thank you. Questions for Stas? Anyone here? I have one. What's the total cost of this entire set of trajectories?
Let's see, I don't know. Maybe
You don't have to answer. You don't have to answer. So, no questions. Thank you very much.
Thank you.
That concludes. That concludes part 1 of session 5. A couple of announcements. First of all, is there anyone belonging to session 5 that has a 2-minute talk at the end? Anyone? If not, then we might be able to add a minute to the talks in session 5 if we don't have any 2-minute talks. And the second is that you are all invited to stick around here for a photo op that's going to take place very soon, right in this place. Any other announcements, Bill? Now, right? Photo op is right now. Thank you and bon appetit. We have a series of additional campaign-related talks here that will start with a talk by Brent Barbee about spacecraft mission design. And Brent is standing next to me. He's ready to go. And I'll hand over the mic to him.
Okay, thank you, Nahum. Sure. Okay, so today I'm going to be talking about some spacecraft mission design options for dealing with the 2017 PDC hypothetical asteroid threat that we've been studying here at the conference for the past several days. I'd like to acknowledge my co-authors who are listed on the title slide. Bruno, Josh, and Jacob are at Goddard Space Flight Center with me, and of course you all know Paul Chodas, the designer of our hypothetical threat scenario. Okay, so I want to open with a quick point. Asteroids like 2017 PDC, our fictitious asteroid, exist in real life. Here is an asteroid, 2006 WT1. I've shown a screen capture of its information from the Small Bodies database. It's a potentially hazardous asteroid. And if you check out its orbit, it's awfully similar to that of 2017 PDC. Similar same major axis, similar, almost identical eccentricity. Not quite, the real asteroid is about twice the inclination. It's a little bit bigger, age of 20, and a pretty low minimum orbit intersection distance with the Earth. So keep in mind, the scenario that we're studying at the conference is very realistic, and it certainly could happen in real life. Okay, so just a quick review of some of the properties of the PDC threat object. The size could in principle range from 60 to 385 meters at the very, very maximum extents of the possible values of absolute magnitude and albedo. But within that, a reasonable assumed size range is about 1 to 300 meters, which has already been discussed in the press releases that Paul has given. The bottom line is that there's about a factor of 30 uncertainty in mass, and this will strongly affect the size of the deflection campaign. A quick note about what tools we're using to do the mission analysis. We developed a custom grid search tool that can find linked ballistic campaign trajectories for both characterization and deflection or disruption. We also use NASA's Evolutionary Mission Trajectory Generator, or EMTG, which uses genetic algorithms and monotonic basin hopping to optimize trajectories. And we've recently developed a new objective function for the optimization that allows the software to directly optimize asteroid deflection away from the Earth This is a very new development, so I don't have a lot of specific results to show on that just yet, but we're in the process of generating those. And I'll also show a case where I've reproduced one of our ballistic results in the Deflection app on the CNEOS website. This is a broad summary of all the different possible trajectory types that we might conceivably use. In the talk before lunch, Stas showed several examples of these. I've underlined the classes of trajectories that I'll touch on today. But in broad terms, we can categorize the trajectories as either using chemical propulsion, characterized by impulsive or near-impulsive maneuvers, or solar electric propulsion, where low thrust is applied over a long period of time. And we can also look at different Earth departure postures, direct departure using the upper stage of a launch vehicle, or some sort of a spiral out with low thrust from Earth parking orbit. So these are all the different options, different combinations of which can be used in designing the trajectories. So there's a lot of different options to consider. It's a very large design space. For planetary defense, a few design philosophies. Spacecraft monitoring of the asteroid is critical before, during, and after the attempt to deflect or disrupt it. We need information about the asteroid to inform the deflection or disruption attempt. We need to monitor what happens during the attempt so that if something goes wrong, we can understand what happened and how we might possibly be able to recover. And we also need to confirm what happened afterwards. So having a spacecraft observing the asteroid throughout is highly desirable. And we also prefer solutions for deflection disruption that require only a single spacecraft to succeed. That way, any copies that are made of the spacecraft and launched are there purely for redundancy. When you have a mission that relies on multiple spacecraft just for a bare minimum success, you have many moving parts in the system and lower reliability, more chances for something to go wrong. So this is an example output from our ballistic grid analysis tool. When applied to the PDC scenario, we found that there were several bands of solutions. These bands of solutions have mission design constraints imposed on them. That's why they look kind of sparse. A larger set that doesn't have all the constraints applied can actually be seen on the Near Earth Object Deflection app website if you click on the deflection map button on that web page. Here's an example output from our program where we asked it to look for a campaign involving deflection by a Block 2 SLS. So the deflection is marked in green here, and then a flyby was used to characterize the object before and after the deflection attempt in that example. Characterization is challenging for the 2017 PDC object, as we've seen in the press releases and the subsequent group discussions. It's a large eccentric orbit. It's challenging to rendezvous with in a reasonable amount of time, and time is short in this scenario. But there are more opportunities that exist to do a flyby of the object. And so that's great, but we also have to ask the question of, well, what information can we really get from a high relative velocity flyby of a several hundred meter object? Remember that most flybys that have been done historically for actual asteroids are against asteroids that are tens or hundreds of kilometers in size at distances of several to tens to even hundreds of kilometers at closest approach to the asteroid and velocities of several kilometers per second or more. When approaching a really small asteroid and trying to characterize it by a flyby, how effective would that really be? And what kind of instrumentation would the flyby spacecraft need? So I will show a couple of examples for flyby characterization options in addition to the ones that we've already discussed in the scenario exercises. But first I'll mention a low thrust rendezvous characterization option. This is very similar to the one that Stas showed earlier. The launch dates are just a little bit different. It launches a little bit earlier and it gets there a little bit later. April 2020 is the launch, arrives at July of 2023. And so the arrival date is early enough that this mission could provide reconnaissance in support of a deflection mission that would hit the asteroid during 2024. Now, if we were to increase the power for the solar electric propulsion system and the mass of the vehicle and launch an Atlas V 551 instead of an Atlas V 401, then we could modify the spacecraft to carry a nuclear explosive device to the asteroid and then utilize that to not only characterize the asteroid, but then mitigate the threat. So here's a plot showing the trajectory. It's actually a very, very simple trajectory to get out to the asteroid, similar to the plot that Stas showed earlier. So what are the advantages of doing this armed reconnaissance? Well, we can accomplish pre-deflection characterization, deflection, deflection monitoring, post-deflection monitoring, all with a single relatively low-mass spacecraft. That is a very attractive solution from an engineering perspective. And if we want, we can build 2 of these spacecraft and launch them both to give ourselves redundancy. If the characterization reveals that the asteroid is small, smaller than we thought, less massive, and it can't tolerate the impulse from a deflection, then the nuclear device is simply detonated closer to the object, and we destroy the object. Or if we find out that the object is, that we need to actually stand off further away, and it can still tolerate a deflection impulse, then we can do that. So we can tune the result simply by how close we position the device to the object. And the solar electric propulsion allows the flexibility to launch several weeks later, or arrive several weeks earlier, as Stas's results showed in the previous talk. So here's a quick summary of the nuclear explosive device and the KI mission options. So here I've listed the rendezvous mission launching in April of 2020, arriving in July of 2023. If it uses an Atlas V 551, it can carry a nuclear device to impart a centimeter per second of delta V to the object. Here in the bottom table, I'm showing results for 200 meter, 240 meter, and 280 meter versions of the asteroid, all with a density of 1.5 grams per cubic centimeter. And so what you can see here is that if the object is 200 meters in size, a single Delta IV Heavy launch is capable of carrying out a kinetic-impactor deflection, although the delta V being imparted is just on the edge of how much delta V the asteroid is likely to be able to tolerate before it blows apart, or starts to blow apart, which is about 10% of its escape velocity. Now, for the larger size asteroids, I'll need up to 3 kinetic-impactor spacecraft to achieve a threshold deflection, achieving an Earth miss distance between 0.14 Earth radii and 0.4, 0.5 Earth radii. Total spacecraft mass for those kinetic-impactor missions is up to 18,000 kilograms. By contrast, using the nuclear device, I can achieve a deflection or a disruption for a launch mass of just under 3,000 kilograms, so a factor of 6 less mass. This trajectory plot shows what the early flyby characterization option would look like. This is a ballistic trajectory from our grid search tool. It would launch in 2021 and arrive in April of 2023, so this flyby characterization would be able to support the kinetic impactor missions that I showed, flyby speed of 4.9 kilometers per second. These are the plots for the kinetic impactor mission trajectories. Note that the 2023 launch of the kinetic impactor requires getting the spacecraft within half an AU of the sun. Building a spacecraft that can survive there on short notice could be tough. I agree that if we had more lead time to build it more carefully, we could probably make it survive that environment. The 2022 kinetic impactor launch doesn't get any closer than Venus distance from the sun, so there's a trade-off there. If those opportunities are missed, we have an opportunity to do a late rendezvous for nuclear disruption, so we can launch in late 2022, rendezvous with the asteroid using a SEP system in April of 2025, carry a nuclear device, and destroy the object. Well, it's still a couple years out from its Earth encounter, plenty of time for the tiny fragments of the asteroid to disperse. This would require a next thruster with 20 kilowatts of input power. Or we could do a ballistic late launch option where we launch even later in 2024, June. We arrive in October 2026 with an intercept speed of 2.8 kilometers per second. So we can't deflect the asteroid here, but we can carry a nuclear device and detonate it on a proximity fuse and destroy the asteroid. So in conclusion, 27 PDC is a challenging object to mitigate. Long orbit period, high eccentricity, high inclination, it's difficult to rendezvous with. But high eccentricity actually makes deflecting it at perihelion more effective. So there's a trade-off. Asteroids with more Earth-like orbits that are going to hit the Earth are in some ways harder to deflect, but easier to characterize. And the reverse is true for an object with a long orbit period and high eccentricity, like 2017 PDC. Solar electric propulsion is very enabling and can serve to improve both the rendezvous and the intercept missions. That said, there are a variety of satisfactory ballistic solutions as well for intercepting the asteroid. And if we choose to use a nuclear explosive device via rendezvous, we can deflect the asteroid with significantly fewer launches and much less spacecraft mass than would be required by the kinetic impactors in this scenario. And with that, I'll be happy to take any questions.
Thank you. Thanks, Brent. Some questions for Brent? Over there, uphill.
Hi, Brent. Good
Hi,
talk.
Andy.
How are you? I'm just going to ask, I guess, about a specific, maybe small point. You mentioned that flyby characterization, that we should think about what would be useful and how that can be done. And hopefully we'll have the chance on DART to have a flyby prior to the Didymos encounter. So that might be a good example of something like that, where we're saying we're going to fly by something small and DART is only going to have a camera. But to be able to say, what else would we have wanted, or was that good enough?
That's a great idea. Turning that flyby en route to Didymos into kind of an experiment for this rapid flyby technique, that's a great idea. Do you know offhand how, it's 2001 CB21 is the asteroid, right? I can't remember if that's the designation, but that's the one? Roughly how big is that? Does anybody know? 600 meters. 600 meters, okay. That'd be a great experiment. Yeah.
One more question from there. Dan?
Hey, Brent. Just a question with the flybys. Did you happen to look at any multiple flyby opportunities, whether or not you could retarget and actually look at it, come back by again at least once?
Yes, I did. I didn't show it in the interest of time, but here's a chemical mission that encounters the asteroid twice. So it launches a little bit earlier, August 2019. There's a lot going on here, so I have to parse this. It does a flyby in September of 2020, and then it deflects the asteroid in early 2024.
Cool. Okay, thanks.
Thank you very much.
Okay.
Very interesting. And we move to an update on the Neo Shield by Albert Falk.
So thanks for the introduction, Nahum. And
You're welcome. Microphone.
Oh, I need to stay closer. Okay. Okay. In my role as coordinator of the Neo Shield 2 project, I want to give you a brief overview of the project and a few more details on the achievements we reached so far. Neo Shield 2 is a project funded by the European Union. It started in 2015, 2 years ago, in continuation of the Neo Shield 1 project, and is now focusing on technology development, NEO observations and physical characterization, structural modeling, impact simulations, and potential mission targets. Our project consortium consists of all those partners spread over Europe, and as said, it's funded by the European Commission. Altogether, we are about 75 scientists and engineers, and on the next slides, I will provide you a very brief and condensed summary of our achievements. First, we defined some reference missions which we use to validate and evaluate in the end of the project the technologies developed. There is first of all the fully fledged 2 spacecraft scenario comprised by an impactor and a reconnaissance spacecraft. This is quite a similar scenario like the AIDA concept, and a part that we are targeting is an individual asteroid. Then there is a neo-twist, the neo-twist scenario, which is an impactor-only concept. And finally, there is the sample return scenario. The 3 different autonomous visual GNC and image processing subsystems we have developed have been approached in a harmonized development approach, and independent evaluation has been taking place afterwards. This has been done first for an impactor spacecraft. There's also a dedicated poster outside in the Jupiter room. And here on the picture, you see the Monte Carlo results of the neo-twist scenario, where you see, for example, the red circle here, which marks the requirement of a missed distance less than 50 meters. And all the blue pixels here point out the simulated impact performances. You see we are well in line with the requirement, and all this validation has been taking place on a real-time validation chain, including the space target processor. On the right-hand side, you see also the optical stimulation chain. A similar approach has been taken for the reconnaissance spacecraft, mostly focusing on the critical modes, meaning the close approach, inertial hovering, and the body-fixed hovering in order to separate a lander unit or initiate a landing sequence. Last but not least, the sample return scenario has been selected to assess a full landing scenario for improved scientific outcome. And this scenario as well has been tested in a real-time test facility, which you see here on the right-hand side. There is, for example, this robotics facility which has been used to validate the performances, and it employs asteroid surface mockup. On the lower side, you see the optics facility, which is used to validate the algorithms or the algorithm performances using a synthetically generated image, which is then captured by a real representative camera. The same facility has been used to develop and validate the orbit determination algorithms in order to assess the beta factor. There is also a related poster outside, which you might have discovered yesterday. The goal with this algorithms is to quantify in a very short time scenario the impact effects and to determine how successful the effect was. What we were able to demonstrate is that with consideration of high fidelity algorithms, the image processing and the dynamics, that we achieve a 3 sigma performance value for the beta determination of better than 0.3. Next, we have developed a novel sampling device featuring a powder-actuated bolt. This device uses a first fluidizing activity, which rinses with a gas flow the loose regulus layer from the top surface down into a first selection chamber. Then it actuates the bolts, and a second fluidizing process then rinses the broken rock material into a second separate selection chamber, collection chamber. Okay, now I'm coming to the scientific results. In terms of physical characterization, we have performed a lot of observations and also pre-recovery activities using PanSTARRS-1 data. We have obtained light curves and phase curves of numerous objects using smaller telescopes and also larger telescopes like the TNG and the NTT, where we obtained photometric colors and visible spectroscopy. As a first result, you have heard Simone's presentation 2 days ago already. From the entity, the first outputs we can say is that we almost doubled the size for smaller objects in the literature. On the right picture you see the results of the classification performed on those observed objects, and it seems that there is an abundance of A and D types asteroids for smaller objects in respect to literature for larger sizes. Alan's talk yesterday about the statistical analysis already has shown that he has found a method to identify how infrared observations can reveal insight into material properties, mineralogy, especially metal content, and the dependency of thermal inertia from rotation period can give us some clues on surface structure. Moreover, the performed ejecta fate modelings have shown that there is an environment clearance mechanism possible, which helps to identify safe locations during and after impact in the vicinity of the asteroid. Then we have established a NEO-properties portal where we provide at this web address in an open access policy all the observation and characterization results. Furthermore, the developed observational tools which help to coordinate and prioritize the observational targets are also accessible there. And finally, the dynamical web interface also provides mission opportunities tables, including NEO-accessibility information, which help to identify suitable targets for scientific exploration, meaning rendezvous or return missions, and deflection demo missions. So concluding my talk, we have contributed key technologies and majorized them for kinetically impact, proximity operations at and landing on small NEOs, meaning 300 diameter and less. We have developed fast and precise orbit determination techniques to assess the beta factor in short term. We have developed a novel sampling device and obtained numerous physical properties of small NEOs, and established or found a method to derive mineralogy, metal content of surface structure from infrared observations, and also performed impact ejector dynamics modeling in support of real demo mission scenarios. So that's it. That were our contributions to the overall effort to prepare for the next major threat, and I'm happy to take questions.
Thank you. Any questions for Albert? One up there. Paul.
Very nice talk. I just wanted to ask a little bit more about the sampling device. Can you go into a little bit more detail how that works? Will it work on a rocky surface? And what depth will it actually sample?
Basically, that's the requirement to work on more solid rock material to break up the rock and allow to collect samples from this broken up material. Maybe I can bring you in contact to Martin, who has taken part in the development of this device and is also here. So maybe I can show you later on.
Yeah, that would be great. It'd be very interesting to see what the depth, how far down you can.
I'm not aware of the, let's say, breakup distance, which is possible.
Thank you. Any other questions for Albert? I have a question. You're talking about the development of technologies. Does this involve development of new technologies or adaptation of existing technologies, or both?
Let's say, I think it's both. It's adaptation of existing technologies for these new cases where navigation and operation very close to small objects is necessary. They require, let's say, more complicated solutions because gravity and disturbance torques and forces are quite similar. And therefore, navigation and control makes it more complex.
Thank you very much. And continuing with the new twist, elaboration with Line Drube. Thank you.
Thanks. Good. Thank you. So I'm going to talk about the new twist mission concept. And it's a concept that started about 3 years ago, based on the fear that AIDA wouldn't get the funding in time. So there's quite a few similarities between the two concepts. And this one is meant to be somewhat cheaper with only one launch. So as it's so the idea of this mission concept is that instead of changing the rotation of the binary, then you actually just change the rotation period of an asteroid itself by impacting it off the center of mass. So here we're using Yoshikawa. So impacting it at a distance from it, impact here, you get an arm and change the rotation rate. And then the ejector, the more ejector you have, the faster you will rotate it. And therefore, from that, you can get the beta factor, how much ejector you get. So the idea is that we would like to use a well-characterized target. And for us, from the one that's out there right now, Yoshikawa is the only one that's really relevant. Also because it's very, very easy to measure the rotation rate extremely precisely from Earth due to the shape. Another thing with the shape is also that you can almost get a completely perpendicular surface area quite far away from the rotation rate, and therefore get ejector almost directly backwards. So from our calculations, we'll get, if we just assume no ejector at all, you get a minimum of about 4 minutes of change in the rotation rate. And you know the rotation rate of Yoshikawa down to milliseconds almost. And within a couple of years, you'll be able to measure the change down to seconds. So 4 minutes is very, very easily measured. So the mission objective is with the same as AIDA, technology demonstration of a kinetic impactor and quantifying the momentum transfer. And another thing is that there's mission opportunities every 3 years. Some years are, of course, better than others, but there is every 3 years. So we are a small team from the New Shield project, where we at DLR has been doing some of the scientific investigations. Then we have Astrium doing the spacecraft design, Dimers doing trajectories for us, and JPL, or Secret Eagle, who's now at JPL, has done impact point optimization and post-impact risk assessment, just to make sure that we don't make it into a dangerous object after. And then we have had Steve Swartz doing calculations on density effects on the beta. So the mission architecture, it can be done in 3 different budget groups. One is that you just have one impactor impacting there, and you observe precisely where you're going to impact via just images that you send back to Earth, and then you measure the rotation change from Earth-based observatories. The second one is that you have the impactor and a flyby vehicle, which is ejected from the impactor sometime before the impact itself, and it will fly by and observe the impact itself, where the location is, the ejector coming out, the cloud, and therefore also the direction of the ejector. And then on, the third possibility is that if there's anyone want to put some nano satellites onto the impactor, then you can also get these chasers that will continue an impact after the impactor itself and have about half a minute's leeway so that they can observe the crater itself and possibly and the ejector cloud from inside the cone. So this method could be done from one country, or you could divide it into several units for international collaboration. So we've done some impact optimization, trying to figure out where is best to impact it, and we have found this area around here to be the best point, because you don't want to change anything on the surface, because if you change too much of the structure, for example, impacting close to the very large boulder here, you'll change the moment of inertia, and therefore also change the rotation rate. So we found this as to be a very sweet spot, and the precise point depends on what you expect from the beta factor, because if you get out here, you get a bit of an angle on, you get more of an arm, but you'll get ejector going out to the side, so sort of the optimal point depends on where you expect it to be. So, and as some might have seen, so this is the change in period down to 30 minutes, that if you have a beta of 5, now we have tried 1, 3, and 5. So at 5, you can see here the different areas of the asteroid, how much you will change the rotation rate. And out here, depending on how well you know the impact point after you have impacted, from your last images, I should also say the flyby vehicle is used as a relay station for getting data from both the impactor and the chasers, so that you have a bit more time to send it back. So you have fast transfer there. But here, what you see here is that these areas where it's best, and depending on how well you know your impact point here, you know precisely where it is, how large your crater is, and these are that afterwards, after that you're not precisely sure where it is within radius of 25, then you can see here these are the change in period, and if you get about half an hour, you know it's possibly around a beta of 5. If you get around here, you can get a beta of 3, and if you get it down to 6 minutes, it's probably around 1. So you can kind of get, depending on how well your location is, you can get a very precise measurement of your beta. But go read the poster. Other than that, here you see the observability of Itokawa. So this is the absolute magnitude, being very bright up the y-axis. And what you see here is our different impact times. We have calculated from the next 20 years. We're doing a very large calculation of what is the best trajectories based on which angles and lightning and all that we would like. We find here, and these places here, every 3 years, find good impact times. And we're right now calculating with an impact time of about 8 to 9 kilometers per second, mass around 500-600 kilos, and so on. And you can get very quickly the period change within the same, right here. You'll get a good estimate, and then next time it gets around, you'll get an even better down to below 1 second. So we've right now just also calculated if we could do a second flyby. Someone mentioned it here before. And we realized that we could use, possibly, if we find that this is beneficial, that we can use a 2 to 3 resonance and come back 3 years later. So impact here and then come back around here. We're using an extra delta V of 2 to 400 meters per second. Or we can use a 3 to 5 resonance, come back 5 years later, around the same. And in this case here, you can get the extra flyby for just 20 meters per second, extra delta V. So we're going to figure out if that's worth it, if that's scientifically enough benefit to the cost of this. Other than that, we've done recently some work on the thermal emission at the precise impact times to see if in case we want to use a thermal infrared imager on the chasers or the flyby vehicle. So we have done some calculations on it using different thermal inertias on the dusty areas versus the other area, the rough areas. Then we have also been wanted to get some estimates of the crater size and what we'd expect from observability of the ejector. And for that, we have used Hausen and Holzapfel's formulas and their targets they've been using. And since that was took a long time to calculate that every time we wanted to change the parameters, we decided to do this pull-down menu where you could pull down with different targets and change everything, how big your density of your impact, everything. And then we can get out idea of the crater. For example, here, this is based on these calculations, what we'd expect. And also how much the ejector cloud, the magnitude would be based on this. And if anyone need to use similar, you can download it here. So, so depending on your minimum size, you can see the change in your magnitude, apparent magnitude seen from Earth, here based on before and after. So, but it's very rough calculation, so just to get an idea. So in conclusions, the new TWIST mission will be able to determine some the beta factor to a certain degree and give real measurements to test those impact models, all the standard things, enhance our understanding of asteroids, and so on and so on. And if you want to know more about our mission, you can see some of our papers that's been out there. Thank you.
Thank you. Any questions for Line?
Chapman.
Oh, here, down here.
Yeah, if I understand, this assumes a homogeneous interior of the body.
Oh, I'm so happy you mentioned that.
Wait, well, let me just say that you have Itokawa, and if things the size of the head of Itokawa or half the size are distributed asymmetrically within the larger portion,
okay, inside, yes.
How do you take account of that?
Well, there is of course art, but that Laurie came out some time ago and talked about the change. So they measured the Yorp spin, and they could measure that it was not as you expect if it was a dense, homogeneous density. So they suggested, based on the change they were seeing, that the head was was somewhat heavier than the body itself. I'm assuming that was because this is probably a one piece, while this is with porosity in it. And they said, based on if this was true, that this is the head was heavier, then you would actually move the rotation axis with 21 meters towards the head, which will change both the moment of inertia as well as your arm that you're getting in. So we tried to calculate this doing modeling. This was what Steve Swartz were doing, and calculated that if you move it based on where we're going to impact, if you move this, the effect that the moment of inertia has on this is that it gets to be about 10% higher increase in moment of inertia due to the fact it's off rotation axis, or it gets further in. But at the same time, because the arm gets longer, so you push it in here, so it gets more difficult to rotate, but your arm is longer, and it got about 17% longer in this case, but they're going opposite directions, so in the end you ended up with a change of 6% in the beta in toll, so it kind of made up for it.
Well, that's one specific...
Yeah, in this area where we... Yeah, so that's the question. There is, of course, always uncertainties in all measurements, but how big are they?
Well, we just don't know the interiors of these bodies.
But so no, of course not. But they measured. So depending on how much you believe in the Yorp spin-up effect, this should be. This could be a good explanation of the inside. How the density is. But yes. There's some uncertainty in all.
Things to discover. Any more questions for Lina? Thank you very much. And a natural extension to the same thing is, how would you design such a mission? And so Kilian Engel will tell us the story about that. Thank you.
Okay, so good afternoon. Thank you for the introduction. As just mentioned, I'm here to give you an overview of a design study that we're doing at Airbus in the NeoShield 2 project, together with all the partners of the consortium. Just a quick overview of that. Basically, in the previous talks, you've heard about what NeoShield 2 is about, and also the general concept of NeoTwist and the observation principles that are being proposed for that. So that kind of makes the introduction largely redundant. Just wanted to reiterate, we're talking about a Kinetic-Impactor demonstration mission. The hope is to come up with a concept that allows a relatively low-cost mission or cost-effective mission while retaining most of the utility of the full-fledged two-spacecraft mission. And like any such mission, the two main objectives, of course, are demonstration of the relevant technology and then measurement of beta and gathering some information about the impact physics that we expect in such a collision. Okay, you've seen this image in the talk just now, so I'll just go through it very quickly. So we have Itokawa as the target, an impactor which also functions as the carrier spacecraft for the other sub-spacecraft. Then you have in blue here the flyby module, which separates prior to impact and passes the target roughly parallel to the impactor at a safe distance. As Lena pointed out, importantly, it also functions as a data buffering and communications node for the other vehicles, so receives all of the mission data and retransmits it to Earth after the event. And of course, its main observation functionality is to see the ejecta cloud that we generate. Then there's potentially also these chaser 1 or 2 spacecraft here that are ejected in anti-approach velocity direction and follow the impactor down the terminal trajectory. And with that, like Lena pointed out, we hope to maybe get a look at the crater. And what else is here? Yeah, so the spin change, as has been mentioned, of course, is then observed from Earth. This is also alludes to what Lena said. There's 3 implementation options, so impactor only. Then if you add the flyby module, you get some information about the direction of the momentum carried by the ejecta cloud, hopefully. And if you add on top of that the chasers, then you should get some very good information about the impact location and also the volume and morphology of the crater. So depending on how much money or how many partners you have, you could go for any of those 3 and have a useful mission, we think. Okay, so one of the big design spaces for this concept is the observation geometry. I won't go into the details of it, but some of the factors that come into play are, of course, the sensitivity to the, or let's say let's start by saying it's defined mainly by the offset distance, so your closest flyby distance and the time that you arrive at that flyby closest distance with the flyby module relative to the impact. And the distance in particular is sensitive to the constraints you have there, the sensitivity of the field of view to uncertainties in the ejecta dynamics. So you've got to make some assumptions about that, but of course we're trying to measure that, so we don't know a priori. Then the apparent size of your observation target, of course, the closer you get, changes more during the flyby. The azimuth rates go up, and of course you're more sensitive to any errors in your approach trajectory. So most of that pushes you towards further away flybys, but of course then the size of the optics required for a given performance limits that. So you've got to find a compromise. And right now we're looking at a flyby distance of about 70 kilometers, with reaching the closest approach very shortly after the impact. We've got an 8-degree field of view and a maximum azimuth rate of about 7 degrees per second. And just to give you an idea, with certain assumptions about the expansion velocity of the ejecta cloud, what that looks like. So you have at 0.8 seconds after the impact, you've got this ejecta cloud. The little white part is the actual asteroid. The far side is colored in red, so you can see at the beginning, you can still kind of see into the cone a bit. Then at 2 seconds, you pass it directly looking at it from the side, and at 10 seconds, you're kind of sort of looking back and past enough to get a bit of information about the third dimension. And if that works, then I can just do a quick, I don't know, video of that, just to see what that looks like. The box is the field of view of the camera, and you can see the scale changing, of course, because you're looking at a expanding ejecta cloud. Okay. Okay, so next I'll just go through quick what we have on the vehicle design right now. It's all still pretty early stage. We've got the impactor / carrier, and we've based that on an updated version of the Don Quixote concept. So we've got a mission module on the top and a large propulsion module, which is a reuse from Lisa Pathfinder. All of that's launched on a Vega, and we get a impacting mass of about 550 kilograms, which includes the propulsion module, which is taken to impact for additional mass. And as I said, that's not the focus of the work we've done so far. What is the flyby module, which is this observation module deployed prior to impact. The drivers for that are obviously gathering some high quality imagery in a very dynamic situation, both a dynamic target and a dynamic observation geometry. And all of that with quite a bit of uncertainty in how we approach and how the observation target reacts to the impact. Then in addition, we've got to handle the data coming from the other two vehicles and try and squeeze that into a fairly small package. For the payload, we're looking at a relatively small camera with an aperture of below 10 centimeters, relatively wide field of view. That's why we need to get close, 8 degrees, 2K by 2K detector. And for the pointing, since we have this high azimuth rate, 7 degrees per second at the peak, we're proposing to use a pointing mirror, which would then track the target during the flyby in 1 degree of freedom. And how you do that is illustrated here. So since we don't know the approach geometry precisely, there's a number of errors in the offset distance related to the release conditions and also the approach trajectory of the impactor. One thing you could do, you could design a very wide field of angle or wide field of view camera, but that would be giving away imaging resources. So we have during the approach a navigation phase where we use the payload camera to determine our approach trajectory and then switch into an open loop during the close flyby and track the object based on the improved trajectory that we've been measuring. Here's a view of the current spacecraft configuration. So that's for dimension, it's about 1 by 1 by 0.25 meters. You can see the main prominent features, of course, are the high gain antenna for comms with Earth, and then two medium gain antennas for the communication with the other vehicles, and the camera pointing mirror protruding from the side. Okay, I won't go through that, just to say it's about 100 kilogram spacecraft at this point. It's got all the basic functionality, 3-axis stabilized, and a fairly capable comm system, of course. Then for the chasers, this is a lot more rudimentary concept at this point. We're not that far into that, but basically the drivers are a pretty small target, the crater. Quite a bit of uncertainty in the imaging geometry. One of the challenges is to get the imaging data out more or less in real time to the flyby module, since the vehicles will likely be or possibly be destroyed by impact. And we need quite a bit of delta V for separation. So like I say, this is not too detailed yet, but the idea is to have a single momentum wheel which stabilizes the vehicle in the attitude that it's deployed. And since it's following the impactor down the terminal trajectory, it doesn't really need to the point for imaging the target. Yeah, so this is, again, won't go through all of it, but right now we're at about 25 kilograms. We hope to bring that down a bit. Certainly unusual for such a small vehicle, is a pretty capable propulsion system, because we do need to have a bit of delay between the impact of the impactor and then the arrival of these vehicles, and a quite capable data, communication system to get the data out in real time. Okay, to wrap it up, basically what we've been trying to do is come up with a mission concept that offers good utility at reasonable cost for a kinetic impactor demo mission. We try to achieve these advantages, as Lena also pointed out, by applying a measurement principle based on the rotation of the asteroid and observations from Earth, and replacing the large rendezvousing spacecraft with two sub-spacecraft that we deploy. So far, we haven't found any showstoppers. We think we have a useful mission, but of course we're going to keep working on it, and we're interested in resources and partners to do that. With that, I'll be happy to take any questions. I have 8 seconds.
Yeah, we have time for questions, if any. Okay. Thank you very much. Next speaker is Curtis Iwata, who's going to talk about new mitigation mission assurance.
Thank you very much. As introduced, my name is Curtis Iwata, and my co-author is Dr. Nahum Melamed, and another person back at El Segundo, Kyle Murphy. We studied, the basic idea here is how many launches do we need to make sure that we're confident that we'll be able to deliver a mitigation campaign for an asteroid. So these interplanetary projects that we're embarking on, these are very complex missions and projects, and they're not immune to accidents and failures. And so we're trying to, with this study, we were looking at how many of these types of missions should we be launching in order to guarantee a specific number of missions to be delivered to the asteroid. And here we define campaign reliability as the probability of success, or the complement of probability of failure to mitigate an asteroid as we design it to. So this probability of campaign failure would be the campaign reliability. And I'd like to mention that here I'm mixing reliability and the probability of success. And when I write and say reliability, we're talking more on the probability of success of campaigns. Now, digging a little bit deeper into campaign reliability, we can calculate this as the cumulative distribution function of the binomial distribution, where in this equation, k is the number of acceptable failures. So acceptable failures would be if we need to launch 3 mitigation missions to be successful and we launch 5. The number of acceptable failures in this case would be 2. And some of the assumptions that go into this are that the missions must be independent and that all missions have the same mission reliability or probability of success. Of course, that's usually not the case, but at least for this initial study, that's our going-in assumption. So let's look at an example. For this asteroid A on the right, this gray blob, we calculate that we need 2 launches to mitigate and deflect off course so it doesn't impact Earth. And if we assume that each of these missions have a probability of success of about 60%, then the campaign reliability, first the campaign would need both of these to be successful. And if each one is about 60%, each mission has a probability of success of a 60%, then the campaign reliability or probability of success would be at about 36%. Of course, we would want some redundancy, so let's say we launch 3 instead. In this case, the failure scenario for the campaign would be all 3 of these launch vehicles fail or any 2 of the 3 failing. So then in this case, the campaign reliability would be 1 minus all the probability or all the possible campaign failure scenarios, and it comes out to 65%. And 65% is not necessarily a very high number, so let's say we want 90%. Then in this case, we want to shoot for at least 5 missions, independent missions, to be launched at this asteroid A. Next, we dig a little deeper into what we mean by mission reliability. So this is a specific mission that is going to an asteroid to mitigate, to deflect it, impart some kind of delta V. In this case, I've split it up into 5 phases of the life cycle of the mission, beginning with design, build, launch, transit to the asteroid, and then execute its mission, whether it's a nuclear detonation or a kinetic impactor. In this study, we only looked at the numbers for launch and transit and mission execution because we had some kind of numbers in terms of how many launch failures and anomalies have happened. We could look that up. And also look up the historical interplanetary missions that have occurred. For this portion, we didn't address the design build. We assumed 100% success, and in a future study, we could look a little deeper into that. And then along the bottom, we list some of the sources of anomalies and failures for a specific mission. And then in the next few slides, I'll present some of the numbers that we had from a database from another aerospace person who's been collecting all this success rates and reliability numbers. So first, we'll go into the launch segment reliability. So this tabulates up to 2009. This was a paper back in 2009 by Tomei and Cheng. They've tabulated all the launch vehicle successes and different anomalies. So on the left, we have different launch vehicle classes. Usually for interplanetary missions, we're looking at a medium launch vehicle. Of course, if we're trying to deliver a large amount of mass, we'll also be looking at heavy launch vehicles. And then the paper happened to split it up into US, non-US, and then we also have the global. The main thing that I want to point out here is one, this also includes the launch vehicle failure rate or failures back in the 60s when we were still experimenting with launch vehicles. Of course, if we're only looking at the 3rd generation launch vehicles like the EELVs with Delta IVs and Atlas Vs, this number for the medium launch vehicles will be much higher. But for the purposes of just having a number, we're going to use this 92% number. And I'll be happy to discuss offline about what the real number should be, but this is just a baseline. Next, we look at the spacecraft, and in the next slide, we also have specifically for asteroids. So these are all interplanetary spacecraft missions from 1958 to 2016. And we've had a total of about 150 missions. And we also break out different failures and different anomalies that have occurred. And the main number that I want to focus on here is just looking at the 73% number. It's much lower than the launch vehicle. And when you multiply these out, we see that the spacecraft portion, the space mission portion, is a large driver to this. Next, just for a point of reference, this is all the missions going to comets and asteroids. We've had 17 so far, and there were no launch vehicle failures in this category or subset. And the reliability for all combined so far has been about 66%. And so now we combine the 92% for the global launch reliability and then the 73% for interplanetary missions. And we have a baseline number of about 67%. So 2 out of every 3 missions that we launch beyond Earth orbit to interplanetary are successful. And if we were just to, as a point, if we were to assume 100% launch success, and we assume a very high reliability or probability of success for interplanetary missions, that only brings us up to about 85%, 84, 85%. So now given that, we can now calculate how many launches are required for a specific number of missions that will get delivered. So this chart is a little bit difficult to understand at first, so let me just break it down. First, on the bottom, we have the number of successful missions required. So taking PDC 2017, for example, Paul mentioned that we need 3, so we'll look at this 3 number. And let's assume 67% as our mission reliability. So for all the missions that we send, 1 out of 3 will fail, is what we're basically saying here. And for a given campaign reliability that we're shooting for, of course we want as high as possible. So let's go with 90%. So if we agree to all those assumptions, then we would need to be launching 7 to have, at least 7 to have a 90% campaign level mission reliability. Of course, and then we could look at this a little different way. So now we're holding the campaign reliability or probability of success at 90%. And just looking at this, if we need 3 missions to successfully arrive at the asteroid, and now we're changing the different levels of mission level probability of success. And so if we think that we're better at launching these missions, then of course we would need less in total to achieve the same level of campaign level reliability. And so we had a little bit of time, so we also looked at case studies for the 2015 and the 2017 PDC. Just a quick summary. I wasn't here, but I'm sure most people have lived through this. So 2 years ago, we had a 300-meter long rubble pile, and the exercise participants decided to launch 6 missions. And in post-analysis using the Deflection app, we see that we actually needed 4 Delta IV heavies. And in the exercise, we launched 6, 1 of every kind practically, which is good for independence. And then 4 successful impacts. There were 2 failures, 1 in launch and 1 in trajectory correction. The unfortunate thing was that the asteroid fragmented, and we still haven't had an impact on Earth. So just reflecting back on the charts that I showed you before, so we needed 4 total number of kinetic impactors to hit, and if we had assumed 67% mission reliability, and we launched 6, we were actually running at about 60% campaign reliability, which is not a very comfortable number to live with. Now, if we were to assume 90%, and we wanted 4, and we could vary the mission level reliability, 6 is actually between 80 to 90% mission level reliability, which may be achievable with today's technology and mission assurance practices. And now just looking quickly at the 2017 scenario. We now know that this is on the higher order at 270 meters. And in the pre-analysis, we calculated that we needed 3 Delta IV heavies to move it. And for a 90% campaign reliability, we needed to launch 7. I think we attempted 8. And just for completeness, we also looked at the different launch opportunities. So if we had all these systems in place on day 1, then we only needed 2 Delta IV heavies just sitting on the pad as a minimum requirement. If you wanted a much higher, you wanted to be sure that it was going to get deflected, you would need 5 Delta IV heavy equivalents just sitting around waiting to shoot down an asteroid, which is not really realistic. And then these are just numbers for the second opportunity and the third opportunity. Just to close up some discussion points. The first discussion point seemed relevant when we were writing the paper, but after seeing what kind of precipitated on stage, the leaders decided to throw the kitchen sink at the problem. And I guess having seen that, maybe this first discussion point about what should we take into account, the question, I guess, is more of, do we have the industrial base? Do we have enough rockets? Is our kitchen sink big enough? Next, what is the acceptable level of campaign failure? Is 1 out of 10 attempts in deflecting a NEO acceptable, or does that need to be higher? How do we deal with fragmentation and complication in trying to deflect this mission? And how does accelerated development affect the mission reliability? And so in summary, we developed a method to start looking at what does it mean to be reliable at a campaign level. And as a point of reference, we looked at historical data for launch vehicles and interplanetary missions, and we applied this to the PDC 2015 and 2017 in hopes that it might be helpful in the decision making. Of course, there are multiple directions that we could take this. I think the current thought that might be interesting is what are the policy implications? What are the coordination? What is the industrial base that we have today? Can we actually, if this were to hit us or come towards us, can we actually address that? And with that, I'd like to acknowledge Edward Tomei, who's been very helpful in providing us with how to calculate some of these reliabilities, Dr. Ehler for being one of the reviewers, and the other editors and reviewers as well. And with that, thank you very much.
So we have already 2 questions. So one here.
Yeah, I think this is a very interesting approach, and there's 2 things I would say. One is, with the kind of disaster that's predicted here in the exercise, I think for sure we'd throw the kitchen sink at it. But your 90% is completely out of sync with the idea that on day 1 of this exercise, lots of people thought that 1% chance of something happening was worth spending a lot of effort. When we know there's a 50% chance of a horrible disaster happening, 90% isn't going to cut it.
Right.
And so that's a very serious, I mean, you haven't carried through to 98%,
Right.
but if you did, that would be a tremendous number of launches.
Right, maybe we would need 100 launch pads ready to try to tackle this kind of problem. But thank you. That would be something to look into. If we want 99% campaign level, 98, 99, how large should the industrial base be to tackle that? Thank you. Yes.
Yeah, very good discussion. The execution anomaly portion of your calculations, seeing that we don't have a good database of asteroid deflection missions, I'm assuming that was not really accounted for in there. And then secondly, that's another aspect of redundancy besides the launch failures and in-flight failures. What's the asteroid's response, and then how do we recover from that if it doesn't go the way we want it to? So.
Right. Yeah, exactly. There's a lot of uncertainty in that execution piece, and there's just not enough experience there. So you're absolutely correct.
So you didn't try to take into account any factor there?
We just assumed for the interplanetary missions, if they were designed to do a specific thing and if they executed it, that was successful in that specific piece. But right, we would want to further refine the mitigation piece, whether it's a KI or a nuclear detonation. We would want some kind of uncertainty bounds there to be a little bit more comfortable, I guess.
Right, thank you.
Thank you.
Yeah, so it looked to me like you were using probability numbers for robotic, largely for robotic missions.
Right.
And that doesn't seem to me really to be the right approach, right? It seems like another approach would be to look at human-rated vehicles and ones that have built in a much higher level of reliability.
Sure.
If you really want, if you want to save, tens of millions of people, taking just a robotic reliability approach doesn't seem to be the right approach.
Sure. And for that, of course, there's a different level of mission assurance, different checklists that would have to go in. And that's another layer that we'd want to look into as well. Thank you.
Thank you very much.
Thank you.
Next speaker is Aaron Reeves, who's going to talk about concurrent engineering methodology for a near-Earth object impactor mission.
Good afternoon, everybody. I'm going to discuss with you concurrent engineering methodology for a near-Earth object impactor mission, brought to you by the Direct Orbital Guidance Effort Team, or DOGE team, from the Aerospace Corporation. I know that's a very concise and original title, so I'll hold your applause for later. So a quick introduction. My name is Aaron Reeves. I was an intern last year for the Aerospace Corporation for the Space Architecture Department, and I, along with 8 of my colleagues and fellow interns across 3 different departments, are bringing you this project. Unfortunately, nobody else could make it but me, but fortunately for you guys, that's more you get to hear from Aaron. So just a quick overview. I'm going to show you guys what mission we were given, the tools that we used to complete our mission, how we actually use the tools to complete them, and what potential ways we can make those tools better in the future, and our final design configurations using those tools. So our mission objective was actually pretty simple. There's an asteroid that could potentially hit Earth, and we need to make sure that doesn't happen using an impactor mission. And it was based on the PDC-17 mission with the given diameter and density and beta value shown above. And it's just kind of assumed that we already know that. We didn't really get into how we would discover it yet. You'll notice that our mission is pretty broad because we had a very short amount of time. So the main focus was our ability to concisely come up with a mission plan and work together to figure out that mission, and hopefully apply more specificity later, because a lot of you all have very relevant ideas that could be applied to our process. So, yeah, I'm sure you all are very familiar with the PDC-17 asteroid at this point, but for our mission, it was assumed that we had about roughly 10 years to plan our mission. It was detected on March 26, 2016, and the date of impact would be in May of 2027. So one of the main tools that we used for our project was the NEO Deflection app. That's just basically a tool that was developed by JPL and the Aerospace Corporation that can give a lot of very specific information for specific impactor missions. There's a lot of good data that we can get from it, and just to provide more context as to the type or the way that we used it, this is a good example. Okay. Yeah, so this is just like an arbitrary mission that that I have for you today, and one of the main inputs was the time of deflection and the transfer time, and these were the main factors used to try to plan around the mission. And so the time of deflection just tells you from the day that your object hit, or that the impactor hits the asteroid, to the day that it was supposed to impact the Earth, how much time that is, and the transfer time is how much time from when you launch to when that impact is supposed to occur. And those 2 times added together is how much time you have from the launch date to when the asteroid was supposed to hit Earth. And another way to look at it is from whenever you detect the asteroid, however long it's going to take you to develop your overall mission, and you subtract that from, let's say, for this case, there's 15 years. It's going to take maybe 3 years to develop the mission, so you have about 12 years to work with your time of deflection and transfer time. And the neo-deflection app will give you the transfer orbit parameters, where exactly this is a 2D mapping of the impact zone. And this is a lot of good information, but we needed to be able to pull all of that data for our use, because we didn't want to just have to write it down through every iteration of our process. So we developed this neo-planning tool. And what it essentially does is if you know what your mission time frame is, and again, that's how long you have before impact, subtracted or taken when you take out the development time, as long as the combination of your time of deflection and transfer time does not exceed your mission time frame, then you can essentially plan your mission around those times. And so what we wanted to do is we wanted to see every possible combination of transfer times and times of deflections that could potentially give us a successful mission. And so what this tool does is it can develop what's called a deflection map for every possible launch vehicle. And that's what you see before you, this beast here. And so this is just a mapping of the transfer times on this side and the times of deflections. And it shows you any place where red obviously represents like you can't, there's no way that you'll be able to send mass to the asteroid. And green represents a successful mission, so any green is you could party, you successfully save the Earth. And yellow represents where you could deliver mass, but it was not quite enough to provide a successful mission. The asteroid is still projected to be within the impact zone. And so this tool is what we use to plan out our mission, so we could essentially look at a mapping like this. This particular one was made using the SLS, which isn't really realistic at the moment. So for the current technology we have today, you'll see a lot more yellow. And we use this to be able to pick multiple days, and this could help potentially with the reliability, because we can know different times where we could send specific masses to the asteroid. And so another major tool that we used was the concurrent engineering methodology, or CEM tool, and that's a massive Excel tool that was developed by the Aerospace Corporation. And what it essentially is, it just allows one or very few engineers to perform concurrent engineering very quickly and by themselves, because it links every subsystem sheet. For instance, if you were to say change how much delta V you want for a specific mission, then it would automatically update maybe your propulsion subsystems to know how much fuel you may need for whatever change occurs. And so each of the subsystem sheets is linked to a database that has thousands of different specific mission components from different missions from the past, so things like computers and thrusters and things like that. And that's where most of the data is drawn from. So you will, so it's really based on a lot of things in the past and reliability. And one problem with the CM tool is it was designed for an Earth orbiting mission, and so we had to adjust it to apply to a deep space mission. And so another tool was the Concept Design Center, and essentially, again, still using it uses Excel, or you can use Excel with it, but it's like being in a room, and each individual, you can have an individual engineer work on a specific subsystem, and you could have everybody working at the same time, and you essentially send data to a specific database. It'll take in everyone's specific data, then send back outputs based off of the data that everybody sent in, and you just iterate through this process until you reach a final design point. And what we wanted to do was utilize the positives of the CEM tool and the CDC to be able to design a mission. And so what we did was we took the utilities of the CEM tool, which is essentially that big database with all of the specific component information, and applied it to the CDC tool. So we took each individual subsystem sheet from the CEM and made it a subsystem sheet for the CDC. So each individual engineer could work on their subsystem independently, and they still had the database from the CEM to work with. And so I'm just going to go over how we would adapt some of the CEM sheets to the CDC. There was a lot, there was about 11 subsystems that we work with, but we don't have time to go over all of them today. So I'm just going to go over these three bullet at the top. And one of the major problems was applying or changing our mission from a Earth orbiting mission to just a deep space mission. So the system sheet, this is basically just, it provides an overview of all of the major system parameters for the mission. And it sends out a lot of data to all of the other sheets so that they know that they have from what point they need to design. And once again, we needed a lot of information from the NEO Deflection app, so we utilized the utility of the NEO planning tool, that Excel sheet from earlier, and we were able to use this button to get specific information from the CEM tool from a specific mission, a specific successful mission from our planning or from our deflection map. And once that happened, the tool would run and it would get the orbital parameters of the NEO, the transfer orbital parameters, and the mass that could be delivered. And then we would design around those parameters. And so just some things that we need to do to improve it, to improve this sheet is get rid of a lot of the sun or the Earth orbiting specific parameters because they weren't really of any use to us, and try to bring more parameters that, or try to basically be able to add our own orbits and things like that in, because we can only use the ones that were specific to the NEO Deflection app. So propulsion, the main concern from the propulsion system here was dealing with uncertainty, because we don't know if, it's very unlikely that the payload that we send to the asteroid would be perfectly on target, and it needs an ability to adjust itself. And so we basically have a way that, or we added a way that we can look at the systems from the CEM database just to provide context as to what thrusters can provide what level of maneuverability. And a lot of what we were looking for was based on the deep impact mission. And so we needed to use the delta V values from the deep impact mission because that's one of the few design reference missions that we have, because as you said, there's not many impact missions that we can draw from, like most of the CEM. And so we had to make sure that our propulsion system could potentially, any propulsion system that we have could potentially provide adequate delta V values for a potential mission like this. And so this is just an illustration from the Planetary Defense Conference from 2015, and it just shows the uncertainty region of the impact with Earth. And it's very analogous to the uncertainty region of the impactor with the asteroid. And we need a way to be able to account for that, or we need a way to be able to know that our payload will be able to maneuver itself if there's a problem and it's not directly on target. And some more things we need to include are sensor capabilities so that we can know how far in advance we could even detect any uncertainty. And we really just need more missions to draw from. And the final sheet I'm going to look at is the structure sheet. Now, the structures just basically says what our payload is going to be made of, and our payload is only consistent of the tracking camera and then just the final mass, because essentially we're just ramming a mass into the asteroid. And so this sheet was particularly uninteresting. What made it interesting to me was the counterintuitive nature of how you're supposed to design the payload. We had to make it as heavy as possible, and telling a group of space engineers to design a heavy payload is like trying to tell a dog to meow or a cat to bark. So in short, what we did was we utilized the new sheets that we made for the CDC in order to come up with two different configurations based off of our times from the NEO Deflection app. And the final payloads were just that, just big ball of mass and the tracking camera. And we came up with two configurations. So we had one where we had a long development time that it took maybe about 5 years to develop, but it was a bigger spacecraft, and it was we were able to deliver more mass. And we also had another scenario where we had a lot more time. So there's a relationship between the earlier you can get your impact, the less mass that you need. And you kind of factor in like how the development time can apply to what type of air or spacecraft you develop. So that concludes my presentation. Any questions?
Questions? Yeah, can we have the mic there, please?
The CM tool that you mentioned is basically a parametric study tool based on real hardware data.
Yeah. So when you pick a specific, maybe you might pick a specific thruster and it'll automatically populate some of like the thrust and ISP values and things like that to see if it will work for the design specifications you need. And so like, that's how it works with all the sheets.
And how far is that automatic? Do you have to pick the components by hand, or do you have a automatic search in the database?
You can, from what I remember, it's been a long time since I've looked at it, but I think you can pick the components that you need. You pick the components that you need. I don't think that there's a search function to pick, like to go through every single one, but if you have some context as what you already want, then you could start typing it in. I believe it'll auto-populate, and then the rest of the parameters surrounding that specific component will be filled out.
Okay, we also have a concurrent engineering facility at DLR Bremen, and we have the same experience doing exploration missions with tools that are completely designed for Earth orbiters. So it's nice to hear that we're not the only ones having that problem. Thank you.
Thank you very much.
Yeah.
Next speaker is Claudio Bombardelli, who's going to compare the ion beam with the Kinetic-Impactor for the deflection on 2017 PDC.
Thank you. All right. Thanks to everybody, especially the organizer, for creating this very exciting problem. We had a lot of fun trying to solving it. And also I would like to thank my collaborators, Emilio Calero and Juan Luis Gonzalo. So just briefly on the deflection method we are analyzing. Since John Brophy already gave an introduction to our method, I will be very brief on that. So it's using ion beams as a deflection method. The beams don't bounce back, they get implanted in material. This is important. It's quite known to the physicists, but not so known to the engineers. So I repeat it here. What else is important to remark here? The disappeared line there that says that the deflection that you can achieve is actually very accurate, and this is the key to this method. Then we have the Kinetic-Impactor, and the deflection physics is also quite basic. It's conservation of linear momentum, and you can, many of you are familiar with this formula here that I think is given by Shears et al. And highlights the importance of the ejecta, which are summarized by this beta factor. So the beta factor is what quantifies the momentum that the ejecta contribute to the momentum transmitted to the asteroid. So one important thing to remark about this beta factor is that we have to be careful in calling it simply momentum multiplication factor, because it's more complex than that. This is true only when the ejecta momentum direction n cap is parallel to the relative velocity of the spacecraft to the asteroid. But of course, in a kinetic impact mission, you are not always hitting tangent to the orbit. And I can show you that actually when you have beta greater than 1, meaning the ejecta are actually playing a role, you can also reduce the deflection. So you can see it here, just a simple sphere. You see here, depending on where you hit with the spacecraft, the ejecta here transmit a momentum in this direction, what you really like here is a momentum in the absolute velocity of the asteroid. So whatever comes in this arc here, it's opposing the momentum you already were transmitting with the spacecraft. So if you want to maximize your deflection, you have to hit here in the augmented ejecta augmented deflection. So you have the ejecta working for you. Actually, there is even a maximum here. So if you hit here and you have a beta equal 2, you have more than 2 times the deflection. So this is a very important thing. So depending on where you hit, the ejecta play a different role. Of course, if you consider a more complicated, well, the other pictures was not shown, but if you start imagining a more complicated shape for an asteroid, like I don't know, Churyumov-Gerasimenko, the comet, then you can have this effect also due to the complex topography that you don't know in advance. So this introduces an important uncertainty in the kinetic impactor. So you need to take into account that. So now let us start to deflect this asteroid. And I don't say anything about the asteroid because we know everything about it at this time. So what I'd like to say is to remark the importance of a rendezvous mission. Since we cannot observe the asteroids from the ground, as we have seen, we need to observe it from space. And I argue that a rendezvous mission will be absolutely necessary and to be launched ASAP, because you cannot carry any deflection or decide about deflecting an asteroid by any means if you don't know exactly how large it is, and most of all, where exactly it will impact on Earth, if it ever will impact. So, so the first thing to do is to design a rendezvous mission. A flyby mission is also very useful. Now there is a problem here, is that the question is a flyby mission enough for constraining the covariance matrix of the asteroid so that you can predict with reasonable accuracy where on Earth is gonna impact? I don't know. What I do know, if you want to constrain that impact ellipse, you need velocity accuracy of better than 0.5 millimeters per second 3 sigma. I'm not sure if a flyby mission can give you that, so this is an open question. Okay, so let us start designing a rendezvous trajectory. We design it low thrust, and this is one of our solutions. I should remark that our spacecraft is much more humble than the one that John Brophy proposed. Here we have 10 kilowatt, a relatively small spacecraft. Our design is based on Dawn, the Dawn mission, that was using 10 kilowatt power at 1 AU. That power plant is estimated to have 150 kilograms mass. We have, in this case, 400 millinewton maximum thrust capability. That's higher than the Dawn spacecraft. And we predict a 1,200 kilograms total spacecraft mass at interplanetary orbit insertion. So with such a relatively high but not too high spacecraft mass, we launch with an Atlas V with 60 kilometers square per second square C3. So we can launch this. Actually, we can launch 1,600. By the way, we have 500 kilograms of xenon on board, and I will tell you later why. So this is one of the trajectory we found. I think it's quite good. We launched on June 2021, and already on November 30, 2023, we are there. 100 kilograms of fuel, roughly. The trajectory is a coast brake, coast thrust trajectory. So eventually, when we rendezvous with the asteroids, we have 300 kilograms left that we can employ for deflection. So deflection option there. Consider a 30-day post-rendezvous tracking. You get the covariance matrix, your covariance ellipsoid shrinking all at a sudden, so you're happy, you know if it impacts or not, you know how far is it, how big it is. So suppose that an impact is confirmed, then you have two options. Well, we looked at two options. First is start ion beam deflection with that same spacecraft, using its own thrusters. And in that case, depending on how large the asteroid is and where it will impact on Earth, you can consider full deflection. You get the asteroids completely out of the impact corridor, or impact point retargeting, which is, if it impacts on a highly populated area, you try to push it in the most deserted places nearby, so that you can make the best out of your spacecraft. The second option is later on to launch a Kinetic-Impactor, but still make good use of your rendezvous spacecraft to measure the deflection that you get with the Kinetic-Impactor. So, one note about eastward versus westward deflection. This asteroid approaches the Earth coming from the inner solar system. That means if you delay its arrival, the impact point will move eastwards. If it was coming from the outwards in solar system, it would be the opposite. So how do you delay the arrival of an asteroid? You increase its orbital period. How do you increase the orbital period? You push in the same direction of the velocity, the simple orbital mechanics. So anything that can push in the same direction of the orbital velocity will have it moving eastwards. We will show that a kinetic impact with a chemical trajectory will only be able to do the opposite, to push it westwards. However, you've seen from Stas trajectories, if you start being more creative with low thrust trajectories, you can get a kinetic impact orbit which is faster than the orbit of the asteroid, so increases the asteroid's semi-major axis, and then you get the eastward deflection that you were looking for. And this is what you get with the IBS. There you can get eastwards and westwards, depending on where you are on the asteroids, in what direction you're pushing. So deflection map, this is for the Kinetic-Impactor. Simple chemical trajectory, C3, 60 kilometers square per second square, maximum launch velocity. You launch all the mass you have, and you hit the target. So good solution here, but unfortunately at 3.38 Earth radii of deflection, beta equal 1 here, sorry, that's important assumption, Atlas 5, but this solution probably is too early. And what we have here is the best we have here for 150 meters asteroids, also the other important assumption. We have already 1.30 Earth radii of deflection on the maximum of this pork chop deflection island. So, yes. Well, the deflection with the IBS, two possibility, Tokyo impact, start pushing with all your thruster to have it eastwards, to have the impact point moving eastwards. Each of these is 1 month push. So if you push for about 15 months, you can get it out in the ocean, and here it comes out of the corridor, so you have full deflection. On the other hand, if you have a Beijing impact, you cannot achieve full deflection with that small spacecraft. However, you can do an interesting retargeting westwards until the Gobi Desert and leave it in Mongolia in 12-15 months with that small spacecraft, and get the tourists to come there to enjoy the impact. So the conclusion, well, the deflection performance of IBS and KI were compared. In general, we have to admit, it's true, KI has higher deflection capability, no doubt about that, by a factor of 2-3, not an order of magnitude, probably. However, the beta contribution to the KI has to be carefully taken into account, because it may be negative if you hit it wrong. Bidirectional capability of the IBS is important, and well, with a small spacecraft we could mitigate considerably the problem. So I think this is good news. Thank you.
We might have time for a very quick question. So there is one question. Otherwise, we proceed. Thank you very much. Thank you. Next speaker is Alexander Payets, who's going to talk about parameter space study of Kinetic-Impactor mission design.
Okay, so good afternoon, everyone. So I'm going to present the work that we've been doing with, in collaboration with Johannes Schoenmakers. So what we want to do in this work is to study the parameter space of potentially hazardous asteroids, and we would like to study at once ballistic kinetic impactors to any PHA. And the aim is to provide preliminary mission design for the whole parameter space of potentially hazardous asteroids. So what we do is to consider at once all the conceivable strictly impacting elliptical trajectories with MOID equal to 0, and this we will call PHA. Okay? And we assume a circular Earth orbit, so increase a bit the symmetry. That gives us the freedom to make the impact happen where we want in our parameter space. And so now the starting point that we take is to realize that the way we are going to parameterize the orbits can actually give us an edge to achieve our goal. So what we want to do is to use the asteroid true anomaly at impact to distinguish between daytime and nighttime impact. So as very well known, if you have a period, eccentricity, and inclination, there are two ways in which you can orient your orbit to have an impact. So here in gray, you have the asteroid orbit, you have the Earth orbit in blue, you have here the perihelion of the asteroid orbit. This is the true anomaly at impact. Here you have the impact point, so it's a node of the asteroid orbit, and here you have the other node, which we are going to call the opposite node. So when you have daytime impact, so going from inside to the outside of the Earth orbit, you have Fi, which is smaller than pi, and it's larger than pi if it's the nighttime impact. So the thing which is interesting is that if you use this parameter, then you don't need to make an assumption regarding the impact node. You don't have to assume whether it's happening at the ascending or at the descending node of the orbit, because actually the physics doesn't care about that. So if you use this parameter, actually you get also the math are the same. You don't need to make a transformation like what you would have to do if you use the argument of perihelion. So if you, for instance, take here I show a unit circle for Fi. So you have the values going from 0 to 2 pi. And what it tells you is, independently of this, if Fi is between 0 and pi, it's daytime disaster. And if it's here, it's nighttime disaster. Actually, you can also find that the opposite node is inside the Earth orbit when it's here. And when it's here, it's outside of the Earth orbit. And that's always true. Okay. What's nice also is that this parameter is well defined, even when you have an inclination of 0. And also, it's truly intrinsic to the impact problem and to the PHA orbit, because it's simply telling you the location of the impact on the orbit of the asteroid. And now what we do is we go a step further, and we actually use this parameter to parameterize the PHA orbits themselves, so we're not going to use the orbital period. The full parameter space actually is just given by the whole set of Fi, E, and I. You just take any Fi from 0 to 2 pi, E from 0 to 1, and any inclination. The parameter space is bounded, and these are dimensionless parameters, so it's very convenient. Any such point, so just take any combination. Any such point is a possible impacting orbit. There are no gaps, and they are all unique in the sense that you don't have to distinguish between daytime and nighttime. And a nice byproduct is that the equations actually become very elegant, very simple, and so you can do analytical studies, and that's what we want to do also. So just to show you, here is how the orbital period looks like in the Fi-E parameter space. So we don't have I here because the period, of course, is independent of the inclination. So just for readability, the palette stops at 6, but really these guys, they are also PHAs. So any point here is a potentially hazardous asteroid orbit. Yep. And then what we want to do is to actually use a polar plot representation. So as a radial variable, we use the eccentricity, and Fi will be our angular variable. So now we are going to have this kind of plots, okay? And there, what's interesting is that really you have a one-to-one correspondence. One point is an impacting orbit, an Earth-crossing orbit, and vice versa. They are all there, okay, for a given inclination, okay? All right, and what's interesting is then if you compare to what we had before, so it means here we have daytime impacts, nighttime impacts. Here it's the opposite node is inside the Earth orbit, and here the opposite node is outside of the Earth orbit. We have a circle here, which corresponds to a period of 1. So all the Athens are here inside, and the Apollos are all these guys. So for comparison, I also took the data from the Minor Planet Center. So of course there is no known PHA which is going to impact the Earth. So as a proxy for Fi, so again, the asteroid true anomaly at impact, we use the asteroid true anomaly at MOID. And here we see how it looks like. So these guys, they are daytime impact, nighttime. And you can, by the way, notice that the inclination can be sizable. And also, see, the period doesn't stop at 6, of course. Okay, so that's the first part. Now, we would like to study the deflection. So what we do is to study kinetic impactors. Because we're going to consider the whole parameter space at once, we take something very, very simple, which is ballistic trajectories only, no maneuvers, no flyby. Okay, so since it's ballistic trajectories and we have a limited launcher performance, the deflection cannot really, we cannot really send our stuff very far from the ecliptic. And since the PHA orbit inclination can be sizable, basically we will, as an initial guess, it's reasonable to take a deflection close to either of the nodes. Because the median inclination of the MPC database is about 10 degrees. So if this kind of initial guess is also used in that work. Then we assume very simple stuff like perfectly inelastic collision, and that the main effect is a small variation of the period, so we don't consider that we change dramatically the asteroid orbit, and that it's going to accumulate and lead to a null-on-track displacement, giving displacement in the B plane, which is what is to be optimized for the kinetic impactor. And this we study in different levels. The first one is analytically, where we focus at the node, so we really study the impact, the deflection, either at the impact point or at the opposite node. And we also do it numerically, then, okay, anywhere, ignoring the phasing. So the important quantities for us are the following. So what we would like to do actually is not really to study how much deflection we have. We would like to identify what's the best geometry at deflection, basically, for each PHA for a given launcher. So it will be dependent on your launcher. So what we want to have is the yearly drift in the B plane, in these funny units, which basically take into account the gravity of the Earth at the very end. Okay, and it requires, so to use this work, it requires having a large enough drift after the deflection, because we neglect non-secular effects, and we ignore the phasing. Okay, and one thing which is very important is the solar aspect angle at deflection, because you don't want to have your camera going in the direction of the sun. So we also study the effect of having a threshold on the solar aspect angle at deflection on the feasibility. Okay, also related to feasibility, what's interesting is if you have a given launcher, you'd like to know if you can go to the opposite node, because of course you can always go on the impact node since it's on the Earth orbit. So here we show the location of the opposite node. You can notice that there is a nice symmetry because, again, as I said, with this parameterization, there are lots of stuff which become very simple, so it's kind of natural to have this. And here, what I also show 2 lines is basically it corresponds to the smallest perihelion and the largest aphelion that could be reached with a given launcher. Here it's basically assuming something like the SLS block 1b, so excess velocity at departure of 10 kilometers per second. And on the right, I show the mass, corresponding mass, assuming the same launcher. Okay, and then, of course, then we have this optimization that we do. So without phasing, we have it both numerically and analytically. So with the analytical results at the node, actually, we also make an analytical optimization. So basically, we have formulae that give, so it's only at the nodes, So if you assume a deflection at the node, what's the best V infinity for a given launcher? So just take your preferred launcher for any inclination, and you just have it as a formula. You don't need to solve the Lambert solver. We also have formulae for the drift and for Phison. Okay, but of course, it's at the node, so it's not so, I mean, it's an approximation. Okay, and then we also have the optimization, numerical optimization without phasing. So that help us identify what the actual best yearly drift could be. And we have there different results for different inclinations, different cuts on the solar aspect angle. And what's nice is to have both, because then with the analytical results, you can start understand and highlight different properties, mission types, and what to expect. So on the right, for instance, this is numerical results for the yearly drift and for the solar aspect angle. And you can see different types of missions, actually. And if you put a cut on the solar aspect angle at deflection, then you see there are differences between daytime and nighttime impact. You see here, there is a region that appears where actually it's now all of a sudden you start to prefer acceleration along track, and all of the stuff like that, which can be understood better thanks to the analytical results. Finally, there was also a previous study which included phasing, so we can compare with them. But that's something also we would like to continue doing a bit more, see the differences. So for more discussions, more results, please have a look at the proceedings. And I'm more than happy to discuss. Thank you.
Thank you. Any question on this topic from anyone? No? Thank you very much. So we have one more presentation by Jean Timor, followed by a 2 minutes poster presentation. And the next talk is going to be how we characterize via solar cell.
Hello, thanks for your patience for the last long talk today. I'm going to talk about solar sail-based characterization of asteroids using projects and data that have been related to our projects. I'm just doing the system task here and want to acknowledge my co-authors, Peloni, Chariot, and Dachwald, who did all the trajectory computations, and my colleagues from Bremen and Ralf Boden, who's working here, who did a lot of the work on landers and solar sails. So the problem is, when you've seen one asteroid, you've seen one asteroid. So far, all that have been visited close up look different. It's very difficult to find anything to do a classification just from spacecraft work. Of course, there's the spectral information that we get from the ground for taxonomy, the shape and topography and orbital dynamics where you have families, but the connections are still sort of shaky. There's some light at the end of the tunnel for that, but for example on TC3 the composition was quite different from what was expected from the spectra. The radar shapes now give you at least more than one with a similar shape, so they're top-like, cigars, and so on. So all these dots and models need to be connected, and that means you have to go there, you have to look at asteroids, and many more of them than we can do now. So that means it has to be quite quickly, and it has to be affordable. So the next obvious step is to get ground truth, and you can see that in the big science mission, there's no mission that does not go to the ground of an asteroid and at least touch it and interact with it. That's true for the Hayabusas, the follow-up solar power sail, also for ARM or AIM with MESCO 2, depending on whether they're going or not. The way to do that is, well, what can we contribute from our teams? Of course, we have MASCOT, Mobile Asteroid Surface Scout. It's designed to go to the surface from an asteroid visiting spacecraft. It's a small lander that is for the carrier spacecraft integrated at the instrument level, so it doesn't drive the mission necessarily any more than any other instrument. You just have to get close to the asteroid once, drop the lander, and then retreat to a safe distance and continue your observation while the lander does all the risky business on the ground. We've been developing in the lead up to Mascot, and since we've delivered the flight model to Hayabusa 2, quite a few variants of the general design. They're smaller, larger, solar-powered. Mascot 1 has a primary battery. There are different ways of doing mobility and completely different suits of instruments. So this is a very variable and adaptable tool for any kind of mission that wants to look at an asteroid close up. Then we have, when we want to visit a lot of asteroids, the trajectory people in the solar sail community have been very busy over the past 20 years to achieve that, taking the advantage that the solar sail doesn't need a propellant, so it can continuously thrust until something wears out or you're just getting tired of it. This started out with having, for example, 2 fast flybys and 1 rendezvous at the end of the mission. And over time, the tools to simulate these trajectories improved a lot. Our understanding of the sail hardware and the realistic performance improved and got more and more defined. And the most recent results achieve actually 5 rendezvous of more than 100 days. That's comparable to the AIM rendezvous that was planned for Didymos within just 10 years. So every other year, you're going to see a new asteroid. And actually, it turns out that this is a quite powerful method to get around in the inner solar system. Finally, solar sailing as such, of course, you need the hardware. What can we contribute? We had the Gossamer roadmap to develop solar sail technology that was set up in 2009 between DLR and STEC. We had the first step on that was the Gossamer 1 EQM, that was built and qualification tested, but the development was stopped after reaching TRL5, although PFM design was basically ready to proceed. A launch opportunity was available, and it was designed as a piggyback, so you could go with any launcher that is just technically feasible. Okay, now there might be a few criticisms. So compared to real spacecraft, what can a 10-kilogram shoebox actually do? Can it address all the science topics on asteroids? In a way, yes. I just marked it here with different colors to compare with Philae, so a traditional heritage lander that's a real spacecraft, if you like, and our little mascots. So you get information on all the topics. Of course, you have to descope a little bit. You can't put a huge camera into a small shoebox just because of the optical limits of physics. But you can address the very interesting topics that are important for planetary defense and to get a broad overview on many asteroids. Okay, low thrust trajectories. We're going to 5 asteroids in 10 years. Isn't this something that's just one case that you're getting? No, it isn't. If you look here, there's a whole family tree of missions just for one launch date on the bottom left. And for each launch date that you want to have, there are hundreds of possible of these combinations that you can actually also switch between. So you can change your interest while you're going along and go just because of what you learned on the way, go to a different target or address something that's been becoming urgent for some reason that's maybe behind this conference. Okay, we've deployed a membrane in a clean room, you could say. So how do you fly it now? Well, that was the point of the Gossamer roadmap. The technology is still there. We now develop it to do huge photovoltaics, but the mechanics behind it is still available. The people are still there to do it. So the next step would have been to learn control. Bernd Dachwald, one of my co-authors, takes the drawing on the left usually, and a few years ago he used to say, don't design a sail like that. Actually, we think that's pretty much what Gossamer 2 would have looked like, to just test all the sail control methods, find out what's really the best with actual hardware in space, and then pick the 1, 2, 3 best options for the missions that you want to do, and test fly it with Gossamer 3 as an all-up proof test for showing that you can actually do a science mission with a sail and have your camera at the right place at the right time, pointed in the right direction, and so on. Now we integrate that into one spacecraft. First, the Gossamer solar sail. That in itself consists of 5 independent spacecraft. 4 are just necessary to deploy the sail, and you discard them afterwards, which gives you a very nice lightweight sail that's stable as such and doesn't need to be spun or inflated. Is probably also flip over safe, so you can turn in both directions. And all these spacecraft need to be connected at launch to be as one spacecraft and interact. Once they decouple, they become independent and just communicate by a wireless network. Integrating all that with landers, well, we've basically done that since our mascot lander is an instrument for other spacecraft, and we already have this technology to connect 5 spacecraft in one. We can do the same thing with 10 by just adding 5 landers. It uses the same infrastructure. Actually, some of the hardware pieces, like the umbilical connector, are the same design on Mascot and Gossamer, so they're instantly compatible. And in the same way, I'm just focusing here on the electrical interfaces. Of course, you have thermal and mechanical interfaces that have to be designed to make that one spacecraft before you separate, and afterwards you have to be independent and still work in the thermal environment. And we've basically done that with Mascot, which has a very challenging thermal profile to keep cold during cruise and be very warm during operation. Going one step further towards sample return or on-the-ground sample investigation, there are more parts on a solar sail spacecraft that you don't need after deployment. For example, solar panels, or you might have to have emergency propulsion to adjust the initial orbit. You can put all that on the lander and take it along, and then you have all the things that you need for a sample return lander that has to shuttle between the asteroid and your sailcraft 5 times. The big yellow box here is equivalent to the central sailcraft unit that's hidden there on top in the red ring in the Gossamer 1 design. And finally, how big is this spacecraft? This is Gossamer 1 technology performance, so what we just qualified in the last years. The magic number to do all these 5 NEA rendezvous is the acceleration, 0.2 millimeter per second squared. And it's easy to remember with a 50 kilogram bus and payload, which is about the Gossamer bus plus 1 mascot and a little bit onboard instruments for the kind of orbiter. You get a 50 meter square membrane sail, and that gives you the required performance. And if you go a little larger, this is about the confidence limit that we have in the technology, to about 80 meters, then you can take along quite large landers, even Philae size or several mascots. They can drop 1 at each asteroid. They can be different and adapted to the target. Just very quickly, as time is running out, we tried catching PDC 2017 from the 2025 launch date that was in the paper by Peloni et al. We didn't quite make it. We need a lot better sail, but then we get a rendezvous, even then only 3 years late. But to have a good result, we took the PDC 2013, and there we make it. You can see the original 5 asteroids are really close in. AG5 is a little bit further out, and you can just go there. Finally, it was mentioned that there was a 12-degree inclination, and that was considered a high inclination. With solar sail, you can go to any inclination. This is about head-on impacts, was a topic at the early PDCs, and in the meantime was studied for solar polar orbiter. And with that, I thank you for attention and hope for a lot of questions. Thank you.
Thank you. Question up there.
So I was wondering, what kind of aerial densities are you projecting now for these solar sails in terms of grams per square meter?
I don't know that off the top of my head. It's very lightweight material. So the foil itself on Gossamer 1 is a 7.5 micron aluminized Kapton film. Kapton has a little bit higher density than water, so it's very lightweight. The mass of the sail structure as such is about the same as the payload mass. So we're talking here spacecraft that are easily fit the ESPA or ASAP envelope for piggyback launches, so you can tuck them away in any geostationary launch and just fly them whenever you like. So if you want to see 100 asteroids, you just put in 10 piggybacks a year, and then you see them in the next 10 years easily.
Thank you. Any other question? Thank you very much.
Thank you.
And finally, we have a couple of minutes poster presentation by Lieutenant Commander Miyano. The poster is out in the poster room. I think it's an interesting topic, very original. So go ahead.
Thank you. Hi, my name is Thomas Miano. My poster is about the intercepting 10-kilometer plus asteroid. Why do we do this? Because Mother Nature don't have limit, and as we all know, this happened before. So it has to be a big nuclear weapon in order to do this. And the biggest nuclear weapon we had is the Soviet RDS-220, which is the 50 megaton yield, and which weighs about 27 tons. And if you want to launch that from the Earth, you have to accelerate that to at least 11 kilometers per second, and also you have to go through the Van Allen belt, which we haven't done before. Now, if you're going to do this from the moon, you have to accelerate only 2.4 kilometers per second, and you can do that on the surface of the moon. So it's a lot easier. This idea was called mass driver. It was a really popular idea back in 60s and 70s, but we didn't do that. Why? Because we don't have any fuel on the moon. Now, so if you look around, there's a lot of iron on the moon. So what we can do is to accelerate iron electromagnetically to speed of the bullet and use that reaction as a thrust. So then you can make our fuel from the iron. And also on the moon, there are a lot of helium-3, and you can process that to make the deuterium and the tritium to make a thermonuclear weapon. So bulk of the items is already on the moon. Now you still have to bring the plutonium-239, but you only need 11 kilograms. That's the critical mass. So you bring that from the Earth, and you can actually build a thermonuclear weapon on the moon. Now, once we build this system, you can use this system to bring the material from the moon to Earth as well. So this is a dual-use project, and you can bring iron, aluminum, and a solar panel. And if you want to build the 100,000-ton spaceship, which is the size of an aircraft carrier, you can do this using this system as well. So this is worth the investment. Thank you, and that concludes my presentation. Pending questions.
Thank you. Any question for Lieutenant Commander Miyano? If not, you can visit his presentation at the poster office. And with this, we concluded session 5. I was reminded to remind you to load your presentations for sessions 6 and 7 tomorrow morning. And Bill has an announcement.
Actually, too, before I get into the break, which we'll take, and we'll just come back at 4 o'clock. But I just wanted to let you know that we are looking for a host for the next conference. That would be the 2019 conference. And if you are with an entity that would like to get involved in doing that, let us know. Actually, we will get you an application. The Academy has a sort of a formal process for vetting these things. So that would be nice, just making you aware of that. Okay, so let's take a break for 20 minutes, and we'll be back here at 4.